refocused on this. We're going to do 7.4. So here we go. The question on section 7.4 that puts this question on your mind is, how in the world or can we, not where in the world, how in the world, or if in the world, this is possible?
Ooh.
Magic one. And you go, I don't want it to be possible. Let's just stop. Let's just not do it. And the idea is, yes, this is possible. We can do integrals like this if we can do a couple things with them. And I'll talk about those couple things right now. This section is entitled Partial Fractions. And the name implies that we're going to take this fraction and we're going to break it into parts. And we're going to do integrals of. Now, how we break up this fraction into parts is very specific. It depends on the number of cases. The reason why this is possible is there's two rules in algebra with rational functions that you need to know. So here's how. We'll call this the how. How is based on two rules from algebra. Rule number one. Every polynomial in the world, polynomials have positive powers. They do not have square roots. They have positive whole number powers. They're not like x to the -3. They're not x to the 1/2. Polynomials are things like this and things like this. Those are polynomials. If you don't remember what those are polynomials. Every polynomial in the world can be factored as a product of linear and or irreducible quadratic factors. That's a law well, not a law, that's a theorem, approved theorem in algebra. So every polynomial can be decomposed. Decomposed means broken up in different parts. Can be decomposed or can be factored. Into a product of linear and or irreducible quadratic factors. Basically, here's what this says. If it's linear and or irreducible quadratics, it means this. ax plus b and or ax squared plus bx plus c. Every polynomial in the world can be factored as stuff that looks like this and or stuff that looks like this. There are some quadratics that you can't factor. We know this, correct? Hopefully we know this. Some quadratics have complex factors, complex roots, which means you can't factor them with rationals or whole numbers. You can't do that. But we can definitely reduce them into either linear and or quadratics. This is our idea right now. Does that make sense? So when we look at this, you go, hey, look at that. I don't know if I can factor that one, don't really care, but I can definitely factor this one. It's a power 3. Does that make sense? I can factor that. It's going to be linear and or quadratic factors. Rule number 2. Rule number 2 is that every rational function so basically where you have r of x over q of x, where r and x are both polynomials. So for every rational where the degree of r is less than the degree of q, can be decomposed into partial fractions. Now there's one, I know I'm giving you a lot of theory right now and not a lot of practice. Don't worry, we're going to get a lot of practice on this stuff. I'm going to give you one last little bit here. Look up here, let's make sure that we understand a couple of these concepts, okay? First concept. This is polynomial, hence this is a rational. Are we all okay on the terminology? The degree of this polynomial is 2. It's the largest power. The degree of this polynomial is good. If the degree of r of x, the numerator here, if the degree here is less than the degree here, you can decompose this into partial fractions. So far, so good? Mm-hmm. If the degree here is greater than or equal to the degree here, then you do long division of polynomials first, and what that does is that reduces the degree of the numerator to something that is less than this degree. Does that make sense? Mm-hmm. So, if the degree here is less than this, you're good. If the degree here is more than or equal to this, you do long division first, and then it reduces the degree of your numerator, and then you do partial fractions. Those problems are kind of stinky, and we'll see those in a little bit. So little note. No, there's not a shortcut. For degree r of x,
synthetic division.
No shortcut.
Not even synthetic division?
Sure, if it works, if it satisfies the conditions, but that is long division. It's just quicker.
No, just quicker.
For degree r of x greater than or equal to degree qx, do long division first. Are you ready for the next little bit? I know there's a lot of writing right now. We're going to get to this example, I promise, but are you okay with this so far? You kind of have to be, okay? These are two theorems that are proved in mathematics. Every polynomial can be factored into a product of linear and or irreducible quadratic factors. That's these and or these. Every rational where the degree of r is less than the degree of q, the numerator is less than the degree of the denominator, you can reduce that to partial fractions. If you don't have that, you do long division, which brings your power down, your degree down, then you do partial fractions. That's the whole deal. There are several cases that we're going to discover happen with these type of fractions. The first case is by far the easiest case, and we'll talk about the easiest one first, and we'll gradually make it a little bit more difficult and see what happens here. So here's case 1. Case 1. Case 1 is where we have distinct linear factors. Distinct means unique. It means you don't have multiple of the same factors. Otherwise, you'd have that linear factor squared. Does that make sense? So distinct would be like you have x plus 1 times x minus 1 times x plus 4. What you don't get x plus 1 times x plus 1 times x minus 4. That would be non-distinct. Then you'd have x plus 1 squared. We call that repeated linear factors. Are you all seeing the difference here? So distinct means doesn't happen again. It happens one factor and then you have a different factor. So distinct linear factors. Distinct linear factors. Here's what we do in that case. If we have distinct linear factors, then what we can do is we can write r of x over q of x equals, we break this up, and we write a over ax, a1x plus b1. And then we have another one. B over a2x plus b2. And we do this for every different linear factor that we have. Notice, this is linear. You guys with me? It's not quadratic, it doesn't have power 2. This is linear, so basically what we do is we factor our denominator. We see what factors we have. If they're all distinct linear factors, what we do is we make up a fraction for every single one of those distinct linear factors. I know this might be new for you, but are you okay with the idea here? Are you sure? So, we've got polynomial. We factor the denominator. We look at what type of factors we have. If they're all distinct linear, we write a fraction for every single one of those distinct linear factors until we get to the very last one. And we put whatever we have. Oh, you know what? Usually we use A and B and C and so on and so on and so on. So at the very end, sometimes some books do this, A1 and A2 all the way to A sub n. This is just, we use A and B and C and D, but to make our notation a little bit nicer, we'd have the nth actual constant, where A and B and C are all constants. Do you want to see how to do it in practicality? Probably. I want to end with this example, so hopefully we can do this. So, we leave our integral alone right now. We're not even worried about it. We're not even doing any calculus right now. It's all algebra. So we're going to take the integrand here. And we're going to worry about the denominator right now and see if we can factor it completely. Here's what you can and what you can't do. You can't just factor one little thing and assume you're done. You've got to kind of show that it's completely factored. You can't just factor one little bit and go, I'm pretty sure it's completely factored. You've got to know, okay? It's got to be completely factored, which means that we don't ever leave cubics, ever. We sometimes leave quadratics, but you better make sure that if you have a quadratic, it's not factorable. It's irreducible. Are you still with me?
Yeah.
Okay, so first step, number one step. Don't worry about the numerator. I don't care about that. What I care about is factoring the denominator right now. Let's factor that. How can you factor x cubed minus x squared minus x? We'll take the x out. Pull the x out. So if we do that, we're going to get x times x squared minus x minus 6. Still okay so far? Of course you are. It's basic algebra, right? All right. Now, do we stop here? You better make sure that this is not factorable if you're going to leave a quadratic. Is this factorable? Yeah, it is. -3, +2. So we'd have x times x, and it does not matter the order, not one bit, -3, x plus 2. Okay, show of hands if you're okay with that so far. Now here's the idea. What we know then, so bringing this down, is that we have now 4x squared minus 4x plus 6 over what this is. This is the denominator. It's x times x minus 3 times x plus 2. We factor the denominator completely. No saving factors till later, no just ignoring them. We factor it completely. This is factored completely. Quick hit out if you're okay with that one so far. Then you look at your factors. How many factors do we have?
3.
Are they all unique?
Yeah.
Yes.
If they weren't unique, you would have combined them, wouldn't you? You'd have something squared or something cubed or whatever. They're all unique in this case. Are they all linear? Do you see any power 2's there?
No.
So here's what we do next. It's not a hard thing. All you got to do is say what this is going to be equal to. How many factors do you have?
3.
You're going to have 3 fractions. You're going to have x. You're going to have x minus 3. You're going to have x minus 2. We make a fraction for
Plus.
every...
Plus 2.
Sorry, plus 2. I knew something was wrong. You're going to have a fraction for each distinct linear factor that you have. Show of hands if you feel okay with that so far. On the numerator, these are all going to be constants. This is the idea here. So this is going to be a. We don't call this a sub 2. We should call it b to make things easy. And this is going to be c. Are we okay with that so far?
Mm-hmm.
Now, the idea from here is that if you know these things are going to be equal, if you can find a common denominator here, then our numerators would be equal. Does that make sense? If you can find a common denominator. So that's what we work on. So what we do is we go, okay, cool. There's an easy way to do it. If you were to find a common denominator for this, notice that it is going to be this ultimately. That is going to be our common denominator. Well, This is only missing these two factors. This is only missing these two factors. This is only missing these two factors. I call this the cover-up method. It's kind of nice. All you got to do is go, okay, well, cool. Cover up the denominator. And just write the other two linear factors. So if I were to find that common denominator, I'm going to cover this up. Then we'd have to multiply. In order to find the common denominator, we'd be multiplying this fraction by x minus 3 over x minus 3 and x plus 2 over x plus 2. Does that make sense to you? We're not writing the denominator because of this. If I ever get like 3x over x minus 1 equals 5 plus x over x minus 1. If I ever get that, I know that these things are going to be equal if 3x equals 5 plus x. Does that make sense to you?
Yeah.
Of course, we'd have a domain issue with 1, but that's what we ultimately solve this problem with. Show of hands, feel okay with that. So I'm not writing the denominators here because I know that if I get this common denominator, denominators are gone anyway. So I've got a times x minus 3, and then x plus 2. Plus, let's see if you can do the b.
B times x.
X, cool, because I'm going to cover this up. I don't need another x minus 3. I've already got that factor there for my common denominator. I am going to, however, have an x and x plus 2. Still okay? Let's do the c. What's going to be there for the c? Okay, now check it out. What's this whole thing going to be equal to?
X minus 3, x plus 2.
What?
It's going to be equal to whatever this denominator is.
Why is that?
Right? Yeah.
If I have 3x over x plus 1, or x minus 1, whatever I gave you before, it doesn't really matter. And I say that this is equal to 5 plus x over x plus 1. Whenever your denominators are the same, you can solve that problem by setting your numerators equal. You can even do that with the proportion. Cross multiply, you'll see that the x plus 1s are gone. Does that make sense to you? So I would have numerator equal to numerator if these guys are the same. The idea here is that what you're trying to get is a common denominator. You can do this the long way, you really could, but you know what you get? You would get a x minus 3, x plus 2, plus b, x plus 2, plus c, x minus 3. You know what this is going to be over? It's going to be over x minus 3, x plus 2. So basically, this thing equals this thing. Do you see how the denominators are the same here? That means the numerators get set equal to each other. This will be equal to this because your denominators are exactly the same. Does that make sense?
Like cross multiplication.
It's a cross product. That's right.
I get it now.
It's ultimately just a proportion that you're creating. We are ignoring this step because we know it's going to happen. We know that your denominator, if you create a common denominator, your denominators are going to be the same. Look, you're keeping the exact same factors, aren't you? Therefore, your common denominator here is this thing. If we just multiply by the missing factors, we inherently create a common denominator that we can ignore because it's going to be the same on both sides. Question.
Are we going to have to worry about, for the denominator, like x9 equals 0 or 3 or -2 later on?
Yes, but that's the same thing that we would have worried about here, right? And that's in your domain. So, yes and no. We don't create any, I'll say it this way, we don't create any additional problems with this one. Does that make sense to you? Because this already has those problems in it. And when you factor it, you just see the problems. So we have to worry about them, for sure. If we have those, we're going to have what's called improper integrals. That's the next section we're going to cover, okay? So we get there ultimately. But right now we're ignoring that a little bit. I'll be honest with you, we're ignoring it. We will talk about that in the next section, improper integrals, where we go, wait a minute, what would happen if we integrate from, let's see, 0 to 3? Well, we'd have a problem at 0. We'd have a problem at 3. We wouldn't care about the -2, it's not going to show up, but we'd have a problem with those things. We will deal with that. But for right now, I want you to see that we're not creating any additional issues. Do you see that?
Mhm.
These are the same, right? Same domain issues. Do you understand the concept of when I do this, I create a common denominator? And when I do a common denominator, I have my numerators set equal to each other. Do you get that idea? Okay, we're going to stop right there for right now. We'll continue right here next time. Well, we're going to continue. So where we left off last time was, how in the world do we do an integral like that, where a substitution won't work, where it is a polynomial over polynomial, hence it's rational, and where the degree of our numerator is less than, strictly less than, the degree of our denominator. Where it's not, I'll show you what to do in the next, probably the next couple examples here. So if this is the case, what we know by some algebra theorems is that we can reduce any fraction such as this into partial fractions. Partial fractions work in a case-by-case basis. We're either going to have all linear factors, or we're going to have linear and irreducible quadratics, or we might have repeated linear factors, or repeated quadratic factors. That's the idea with this. Now in our case, when we factor it, which you have to do, by the way, you got to know that any polynomial can be decomposed into linear and or irreducible quadratics. So you'll never end with a power 3. It'll be either power 1, like here, 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 or power 2's that you can't reduce, like x squared plus 4. You can't factor that, so we'd be stuck with it. That would be an irreducible quadratic. Are you guys with me? Okay, so in our case we have 1, 2, 3 linear factors. What that means is we're going to create 3 fractions, one for each of our linear factors. The way we do it, we just write each of those linear factors on a denominator and constants, a, b, c, and so on and so on and so on, until you exhaust all of your linear factors. So far, so good? After that, we basically find a common denominator. We want to make this have the same denominator as this, and I explained this hopefully very well last time. If you do that, the numerators themselves will be equal. Does that make sense? So we would multiply this fraction by these 2 factors since they're missing. That's why we get a and then x minus 3, x plus 2. We'd multiply this fraction by these 2 factors. That's why we get an x and x plus 2. This fraction by these 2 factors, x, x minus 3. This is the numerator of this. This is the numerator of this. And now because we have a common denominator, those 2 things are equal. Show of hands if you feel okay with this so far. All right, now we get to continue. And what in the world are we going to do with this? Well,
Make a system of equation.
we're going to have to. We're going to have to distribute all this stuff and organize our variables. So if we do that, I'm going to move quickly because this is, of course, well, just some distribution. So here we go. We'll have our 4x squared minus 4x plus 6. We get ax squared. We get, let's see, plus 2x minus 3x minus ax minus 6a. I want to make sure that I'm right, so can you please double check these as I'm going through, just to make sure I got this stuff right too, okay? Here we'll have plus bx squared plus 2bx plus cx squared minus 3cx. I'd like a double check if you got that same thing. I'm going to double check my work too. Did you get the same thing I got? Okay, now, organize them. What we're trying to do here is we're trying to match up x squareds and x's and constants. So for instance, what I want to do is I want to look at this x squared and I want to look at these x squareds. But right now it's a little bit confusing as to what's going on. So we're going to factor this out. So check it. We're going to have, do you see the like terms I'm talking about? We have a ax squared, bx squared, cx squared. If we factor out the x squared, then what this gives us is a plus b plus c x squared. Do you understand the idea? Hello, yes, no?
Yes.
Okay, so these we've taken care of, our x squareds are gone. Then we look for any of our x's. I see a negative ax, a positive 2bx, a negative 3cx. So we will have, I always do a plus here. We're just going to factor these numbers out. The coefficients are our numbers. So we'd have negative a, we'd have plus 2b, we'd have minus 3c x. So we're looking at this, we're factoring out x, x, x. Therefore, we have a negative a plus 2b minus 3c. Show of hands if you feel okay with that one. Okay, cool. So those are now gone. I always circle them too, that way I don't get lost what I'm doing. I definitely don't want to get lost, and you can't miss a negative here, or you can't screw up the coefficient. If you do that, your problem's smoked, all right? You're done. So we've got to be really careful with our algebra. Lastly, well, this is it. There's only a minus 6a. Now, this is what's kind of nice about this. Check it out. What we know is that 4x squared minus 4x plus 6 equals this thing, don't we? Well, look. If we know, let me have your eyes up here, this is kind of important. If we know that 4x squared, here's our x squared, right? Our x squared coefficients have to equal. So if we have 4x squared and we have a plus b plus c x squared, then what we know is this coefficient must equal this coefficient. It has to equal that. So we know that 4 equals a plus b plus c. That has to be the case. That's why we organize our x squareds and our x's and our constants, so that we can make this jump. So we go, hey, here's an x squared, here's an x squared. This is 4, this has to be 4. That's the idea. Otherwise, these things will not be equal because I have no other like terms. Quick head nod if you're okay with that one. Okay, let's do the next one. Here I have x and I have x. The coefficient of this x is what?
Negative 4.
Therefore, negative 4 equals negative a plus 2b minus 3c. Just match them up. Now the last one's nice. I know that my constant is 6. I know that my constant is negative 6a. Therefore, 6 has to equal negative 6a. So we've grouped all, we've basically factored out our like terms, from our like terms. So we have a plus b plus c x squared. Hey, 4x squared, 4 must match up with a plus b plus c. Negative 4 must match up with negative a plus 2b minus 3c. Positive 6 must match up with negative 6a. Show of hands feel okay with the idea. Now, use whatever algebra you know to solve these things. For instance, start easy. How much is a?
Negative 1.
Once you know a is negative 1, you get to use that fact over here to create a system of equations. So if a is negative 1, then here we have negative 4 equals positive 1. Do you see why it's going to be positive 1? Negative, negative 1, positive 1, plus 2b minus 3c. Or if I subtract the 1, negative 5 equals 2b minus 3c. Also, here's our negative 1 here. So 4 equals negative 1 plus b plus c. Or if I add the 1, what we end up getting is 5 equals b plus c. Okay so far? I'm going to have to move up here. I'm going to rewrite this a little bit. So what I know is that a is negative 1. What I also know is that I've got 5 equals b plus c. I know that negative 5 equals positive 2b. Minus 3c. Okay, so, are you familiar with how to solve systems of equations?
Yes.
All right, so I have a to be and a not to be. How to solve this, that is the question. That's right.
Wow.
That's pretty good, right? Okay. Anyway, what do I do to solve this thing?
You can either multiply by negative 2.
Yeah, I'd multiply something to get some coefficient that's the same on one of my variables. In our case, we're going to multiply this by 2. Therefore, we get 10 equals 2b plus
Negative
2.
yeah.
Yeah, you can do it either way. And then negative 5, and we get 2b minus 3c. If you do that, you'll just have to subtract them. If you multiply by negative 2, you would add them. Doesn't matter which way you do, okay? I'm going to choose to subtract them because I'm going to get positives. Are you with me on this? You guys okay with that so far, yeah? So I'll subtract all this stuff. If I subtract it, 10 minus -5 is 15. 2b minus 2b is 0. 2c minus -3c is 5c. 5c. Are you with me on that one? If you added it, all you end up getting, well, if you multiply by -2 and add it, you get -15, you get -5c. Are you still going to end up with 3 either way? Am I going too fast on algebra? Okay, I hope not. So then c equals 3. Okay, I got a equals -1. I've got c equals 3. Can you find out what b is? Okay, how do we find out what b is?
Input the C.
Yeah, just plug it into whatever equation works for you. This one's going to be the easiest. So I know if a is -1, that's how I found out my two equations. By using a elimination method, I've got c equals 3. That's great. Now that I know c equals 3, 5 equals b plus 3, or b equals how much? Okay, I want to make sure that we are all okay with this so far. It's just some algebra, but I know the algebra can be hard for a lot of people. I want to make sure that you guys are all right with it. So, figure out a common denominator. That way your numerators are equal. Distribute. Organize. So factor out your common terms here. So in our case, common factors. In our case, x squared, x, and just a constant. Set them equal to the appropriate coefficient, and then solve in whatever way works easiest for you. Here, this was nice. This is easy. Use that. Use the easy stuff to make the hard stuff easier, okay? Now that we have a system of equations, use anything that you can do. Substitution, you can do elimination, I don't care. It's all going to work out exactly the same. All you need to be able to do is find out what these letters are. However many of them you have, you need to know those letters. Feel okay with that one? Now, here's what this means. What this means is that our original integral, this is the cool part. Our original integral, because our degree here is less than our degree here, it meant that I could do this. Because I did this, and now I found out my coefficients, check this out, this is the awesome part. Now this integral becomes, hey, how much is our a?
-1.
-1 over x. Plus, how much is our b?
2.
2 over x minus 3. How much is our c?
3.
Plus 3 over x plus 2 dx. If you can make that jump, you understand how to do integration by partial fractions. Do you understand that jump right now? I need to make sure that you actually do. Show of hands if you do understand that jump. The jump is use some algebra, whole bunch of, this is the hard part, this is going to be easy, okay? If I didn't tell you this already, you have learned every technique of integration that we are going to cover here. Then we're going to apply them to improper integrals, so it's going to be a little bit of a change. We're doing this, but this is all algebra. So what this says is, use some algebra to figure out that this is equal to this. If you figure out your coefficients, a, b, and c, then this fraction is equal to -1 over x plus 2 over x minus 3 plus 3 over x plus 2. Hey, look at that. A was -1, right there. B is 2. C is 3. Therefore, since this fraction equals this sum, or partial fraction, this integral equals this integral of partial fractions. So far, so good? It's kind of neat, right?
Yeah.
Now, the rest of this stuff is really easy. Really easy. A lot of times, not a lot of times, all the time with your linear factor, with your linear denominators, you're going to get a whole bunch of ln's. So we don't want to, I never like to write more than I absolutely have to. So when I do this, I do all these in my head because I'm used to doing the substitution. If it takes you some substitution off to the side, do it. But here's the deal. How I do this integral, I'd say, hey, look at this. The integral of 1 over x is ln x. ln
X plus E.
ln
Absolute value.
absolute value. Remember the absolute value? So this integral, the integral of 1 over x is ln absolute value of x. Since it's negative, we just have a negative out front. The negative's that constant. It's a -1. So if we have a coefficient, the coefficient just stays there. Quick head nod if you're okay with that one. Now this one. By rights, you should be doing a substitution, shouldn't you? However, if you did a substitution on this, the derivative is 1, which means you're not going to be changing that coefficient whatsoever. If this was like a 2x minus 3, yeah, you probably have to do a little something with that. I would probably still do it in my head. I do a little substitution in my head. I would know how to do that. I get a 1/2, but you'd have to take that into account. But notice that if it's linear, you can always do that quick substitution, and it's still going to be an ln. The integral is still going to give you an ln. Are you following? Mm-hmm. So in our case, if you had to do u equals x minus 3, du equals dx, okay, that's fine. Do it up to the side. That's okay. I'm going to be a little bit quicker on that because I'm going to assume at this level that you understand how to do this right now, okay? So you could split this up and do it independently of each other. Here we're going to have a plus. What's going to be out front?
2.
And then ln absolute value of x minus 3. Then another plus. This is our coefficient, 3 ln integral x plus 2. Just please, please be careful on this part. Let me have your eyes on the board here real quick. Be careful of this. If you had a 2 right here, or some other coefficient, this is not the correct integral. This is not the correct answer. What would happen is you would do, I'd still do it in my head, but I'd get, okay, du equals 2 dx. That would give me a 1/2. That's what that would be. Can you follow that one?
Yeah.
If you got that, then you're probably pretty good at this, and you're fine. But if you're not getting like, wow, where's it coming from? Then take some time on your own and actually do the substitution off to the side. You can't get these things wrong. Well, you can. I mean, I don't want you to. Don't get these things wrong. The constants and the coefficients are very important here. Show of hands feel okay with this one. So, do you understand that if I have linear factors, I'm going to get a lot of ln's? Because it's going to be 1 over a power, x to the power 1. I'm going to get a lot of ln's here. Now let me change it back. This was not the case, just wanted to show that to you. This was not the case. How do I wrap, oh yeah, sorry, this one too. How do I wrap this up?
Plus C.
Done. That's the whole idea. What's the hard part? Is it the integral?
No.
Heck no. Hard part is this, doing all this stuff. Show of hands feel okay with this one. Now, would you like it if I showed you a shortcut that applies to a lot of these problems, especially the linears? You want to see that?
Yes.
Okay. Remember these numbers. We can cheat. We can cheat a lot. So you have this written down, correct? Are there any questions on this? Should be pretty straightforward. I wanted to give this to you. By the way, sometimes you have to do this technique because you can't do the cheating way I'm about to give you. But with linear factors especially, cheat at it. Here's how you cheat at it. It's not even cheating, it's just being smart. If you want to be smart about this, this is an equation, correct? Mm-hmm. Which means it should be able to give me my coefficients if I plug the right numbers in. So what you do is you leave it in terms of factors, like this and this and this and this, and you leave it just like this. And then you plug in numbers that make your factors go to 0. Plug in values that make your factors go to 0. For instance, when I look at this, I go, hey, and you have to show this little part. If I let x equal 0, check this out. If I let x equal 0, this, yeah, it's -3, but how much is that?
0.
This whole thing is gone. Does it make sense? This would go to 0. If I let x equal 0, this whole thing is gone. Does that make sense? If I let x equal 0, this is a times -3 times +2, because x is now 0. You follow? On the other side, if x is equal to 0, this is 0, this is 0, how much is that? Then we would get 6 equals a times -3 times 2. Let me go over it one more time to make sure you're with me, okay? Plug in values that make some of your factors go to 0. You will have repeated factors, okay? So I'm thinking, hey, the easiest one to plug in, if I plug in 0, this is not 0, this is not 0, but this is. 0 times anything is what, folks?
0.
This whole thing's gone. 0 times anything is 0, whole thing's gone. This is also 0, this is also 0. So if I plug in 0, 0, 0, 6, got it. A, no problem. -3, no problem. 2, no problem. 0, 0, gone. Can you solve that?
Yeah.
So quick. So 6 equals negative 6a, a equals negative 1. Hey, is that what we got?
Yep.
Brilliant. Now, we got a couple more to do. Don't do anything more with this right now. By the way, I always start with this. Always. I always get as many as I can. Sometimes you'll still have to distribute, but at least you got a couple. That makes some of this kind of irrelevant. If you knew what B was, you could find C very easily without having to do systems of equations, okay? So this is a much faster way of doing things if you can. Sometimes you can't. But if you can, yeah, try plugging in some numbers that give you 0, or on some of your big terms here. So big terms, make some factors equal 0. Give me another number that would work. 3 would be a great number to plug in. Do you see why? Okay, so if I plug in 3, I always put what I'm plugging in. So x equals 3, and then I put a little couple dots or colon here. If I plug in 3, let's see. Can you figure out what I'm going to have on the left-hand side if I plug in 3? Notice I'm plugging in 3, not 0. This doesn't go to 6 again. You actually have to plug in the 3. What do you get? 30? We can double check on the 30. Do you get 30? Plug it in. Plug in 3. I want everyone to do this right now. Plug in 3. 30? Triple check. 30?
Yes.
A 30-person check. 30? Did you all get it? So if I plug in 3, I get 30 equals, let's look what happens. Check it out. If I plug in 3, please follow me up here. This is how you're going to get this stuff quickly, okay? Not spend 30 minutes on just the setup. Plug in 3. What happens here? This whole thing's 0. Plug in 3. What happens here? Does it go to 0? No, this is b times 3 times 5. See where the 3 and the 5 are coming from? 3, 5. Plug in 3 here, what happens? This is why we plugged in 3, to make our factor 0. You multiply by 0, it's gone. See how easy that makes it? Now we have 30 equals 15b. How much is b? Hey, we're 2 for 2. It's cool. Why don't you do the last one on your own? What number will you be plugging in if you do the last one on your own? Negative 2. Yeah, very good. Not 2, but negative 2. Be careful on evaluating right here. Make sure you have your signs correct. It's a big deal. You have to get your signs correct here. I know it's algebra, but remember, people take calculus to finally fail algebra. I don't want that to be you. Make sure your signs are right. What'd you get when you plugged in negative 2 over here?
30.
You got 30?
Mm-hmm.
You got 30? Positive 30?
Yes.
If I plug in negative 2, what happens to this term?
0.
What happens to this term?
0.
What happens to this term?
Negative 5.
You get a C, you get a negative 2, and you get a negative 5. See where the numbers came from? Plug in that negative 2. Well, then we got 30 equals positive 10C, or C equals 3. Did we end up getting the same numbers we got over here?
Yes.
Which way's quicker?
This way.
This way's obviously quicker. Does it work all the time? No, it doesn't work all the time. Especially when you have non-reducible quadratics. Because if you have non-reducible quadratics, then you can't plug in a number that gives you 0, like x squared plus 4. You can't do that. That factor is not going to be equal to 0 ever. Therefore, you can't use this technique with that. You can use it for parts of it. So like if you have a linear factor, man, use it for the linear factor. Make that 0. At least it gives you some of those numbers. You follow me? So if you feel okay with this part. After that, man, you go through the same stuff. So let's try this now. I'm going to stick with this technique when I can, because obviously it's a lot quicker. But let's do a different example. Are there any questions on this before I erase it all? Because we're going to need some space for this stuff. You ready? Okay, so new example. Let's talk about x to the 4th minus 3x squared minus 3x minus 2 all over x to the third minus x squared minus 2x dx. Tell me something about this problem that was different, that is different from the last one that we did. What's different?
The degree.
The degrees are different. Remember what I told you about algebra? Algebra said that if the degree here is less than the degree here, then it can be written as partial fractions. I said if. Is the degree here less than the degree here?
No.
No, if it's, listen, if your degree of your numerator is larger than or equal to your degree here. So if this was even a degree 3, we'd still have to do the following step. What we're going to do is, shoot guys, I mean think about it. If your degree here is bigger than or equal to the degree here, that means you can divide it. So we're going to divide it by long division, and then what that's going to do is reduce that degree. So if you have, like the last example, where the degree of the numerator is less than the degree of the denominator, start immediately. Factor immediately and go for it. If you have, like this example, the degree here is bigger than or equal to the degree here, then you have to do long division, and then you'll get to start your problem finding. Does that make sense to you? So we're going to do long division. I don't know if you are that good at long division. I'm not sure that you've seen it in a while, but here's how you do it. We're going to go quickly through it. You can refresh your memory if you want to on some of the videos I have for intermediate algebra. That's where we cover it in the appendices of that class. So here we go. I'm going to need more space. How we do long division of polynomials is we just take our numerator and we divide by our denominator. Now, when you're dividing your numerator, please keep in mind you need at least a placeholder for every potential power of x that you have. So if you do this, look at the board please. If you do this and just go right on down the line, right here you're going to have an error. You're going to have a mistake. Because what happens is when I divide x to the fourth with my x to the third, I'm going to end up getting something here. I'm going to get an x to the third somewhere. So the problem is
0x cubed.
yeah, we're going to put a it's like a place value holder saying, hey, how many x cubes do you have?
0.
I have none of them. Put 0. And then finish it off. Minus 3x squared minus 3x minus 2. So this is the same as this. We got x to the fourth, no x cubes, minus 3x squared minus 3x minus 2, and this is our denominator. So far so good? Okay, let's continue. How we start this thing is basically just the first term divided by the first term. So what do I get when I divide x to the fourth by x to the third?
X.
And then we distribute. We get x to the fourth. Check this out. This is why we had to have a place value holder. We get negative or minus x to the third, and we get minus 2x to the second. It's got to match up. If it doesn't match up, then you've made a mistake. You forgot a place value holder somewhere. After that, what do we do?
Change signs.
Yeah, you can. We're subtracting. You either put parentheses here, or you subtract and you change all the signs. I like the parentheses to show what I'm doing. X to the fourth minus x to the fourth is 0. 0x to the third minus negative x to the third. You can change your sign and make that a plus if you want. This will be positive x cubed. This will be negative 3x plus, negative 3x squared. Plus 2x squared is negative x squared. And then we bring down our next term. Yes, I'm going fast, but you should know at least a little bit how to do this. Are you all still with me so far?
Yes.
Okay, and we start over. How many times does x to the third go into x to the third?
1.
And it's positive 1, so we'll put plus 1. And then we distribute. We get x to the third minus x squared minus 2x. Again, we are subtracting. Again, we'll have parentheses. You either change signs or do it in your head. I do it in my head. X to the third minus x to the third is 0. Negative x squared plus x squared is 0. Negative 3x plus 2x is... And we bring down our minus 2. Now we check again. Does x to the third go into x? Nope. Then this is our remainder. That's our remainder. Here's how you write your remainder. What this says is that this fraction is the same thing as x plus 1, this is our quotient here, plus the remainder of negative x minus 2 over, and when you write your remainder, it's always as your remainder over your original denominator. Are you okay with that so far?
Mhm.
Just don't make the silly mistake of doing this. Please let me have your eyes on the board right now so you see this. A lot of mistakes here are not calculus mistakes. They're sign mistakes. They're sign errors. If you do this and you go, oh, look at that, minus, Mr. Leonard's silly, why don't you just put minus? I don't put a minus there because this sign is wrong right now. Do you know that? That's incorrect. So what I'll do is I'll put a plus with my negative. I'll put this on the numerator. I'll put my plus sign there because you can always add, but you can add later. So here's what you'd have to do to change that sign. You'd actually have to factor out your negative here. Does that make sense? If you factor out your negative, this becomes negative x plus 2, and that's something that we can deal with. So I'm going to, any questions on long division at all? Okay, so this is what we get. So then we know our integral is now x plus 1, no problem. Then look at this. Plus a negative, that's minus x plus 2 over x to the third minus x squared minus 2x dx. So we do long division. What long division does, long division is kind of nice with this. Look at this. It pulls out some terms here that are really easy to integrate. We got an x. Can you do the integral of x? Can you all do the integral of x?
Yes.
It's a piece of cake. Can you do the integral of 1? Absolutely. And then it gives us a fraction where the numerator, the degree of the numerator has been reduced. And that's the idea of division. So our remainder here is what counts. Our remainder is what makes this process a little doable for us. We have this remainder of negative x minus 2. Factor out the negative before you change its sign. That is a must. You have to do that if you have a negative there. Show of hands if you feel okay with that. If it wasn't, if it was just a positive x minus 2, that's fine. Leave it as plus, you're good to go. But if that's a negative oftentimes, I'll factor that negative out. It makes it a little bit nicer to see. Can we move on? So, what are we going to do about this thing? Easy, easy. Maybe split up your integral and see what's going on here. So that's what we're going to do. I'm going to take and make a little asterisk here on this part. I'm going to keep the negative here. Now, don't lose track that you have a minus. When you have a minus, whatever we get, listen please, whatever we get is going to be in a bracket. This minus, we're going to treat like a negative 1 being multiplied onto that bracket. It's going to change all of our signs. Are you following me on this one? So you can think of this, put a circle or put a big bracket right now. That's what I typically do. And we'll pull this off to the side and we'll work with it. So here's our piece right here. At the same time, maybe we can factor this guy. Let's factor this. What factors out of x cubed minus x squared minus 2x? If we got that, we got x squared minus x minus 2. Can I go further?
Yes.
Remember, you don't just factor once and say, I'm probably good. You got to kind of prove that if you have a quadratic, it's irreducible, that you can't factor it. That would be done by doing a discriminant and finding out that it's negative. If you do a discriminant and it's negative, that means you have a complex root and that therefore it can't be factored. So you prove that, or you at least go through it in your head. Now this can be factored. What is it?
Minus 2x plus 1.
Okay, we've done a lot of work so far, but I want to make sure that we're good. So we start the problem off, we look at it, we go, oh, degree is not less than this one, that means long division. I've done long division, I erased it, I know. We do long division. This is our quotient of long division with our remainder of long division. How you write out your quotient is you always write quotient plus remainder. If we have remainder over our first denominator, this denominator, then if it's a negative, maybe factor out the negative. It changed it to a minus, so we get x plus 1 minus x plus 2 over our original denominator. And now, easy, is the degree less than the degree of the numerator less than the degree of the denominator?
Yes.
Now we can go ahead and do this. What I want you to do right now, I want you to write out what this should be equal to. Make your different fractions, however many that you need, and put the appropriate letters up top. And it's a small step, but it's an important step. I want to see that you can do it. How many fractions are we going to get?
3.
However many different linear factors you have, that is how many different fractions you end up getting. What's going to be our first denominator, please? Denominator.
X.
And then?
X minus 2.
And then?
X plus 1.
Does it matter which order you have these in? So if you factor this differently, well, you can't factor it differently, but if you have your factors out of order compared to this one, no big deal. You're going to do the same thing. It's just your pieces of your integral will be a little switched around, all right? Same idea, no problem. All addition's commutative, so we're good. What's going to be on our numerators? What's this going to be?
A, B, and C.
Show of hands feel okay with this so far. We've done a lot of algebra, huh? Have we done any calculus?
No.
We're not going to for a while either. So we got long division, check it. We got this, no problem. Partial fractions, we have it all set up. Remember that when you have linear is power 1. When you have linear factors, we make a fraction for every different factor, and we put constants up top. A, B, C, and so on, and so on, and so on, until we exhaust all of our distinct linear factors. Still okay so far? Now, go ahead, I want you to do this on your own. Create the common denominator. Use the cover-up method I taught you last time. So what I want to see next, I don't need to see one fraction equal one fraction. I want to see x plus 2 equals, and then just give me what this is equal to. Go for it. So use the idea of finding a common denominator. Once you find a common denominator, that means your numerators get to be set equal to each other. If you've already done that, try finding A, B, and C. Use the easy way if you can. If I find a common denominator, what that is that you end up multiplying each fraction by the missing factors in your particular denominator. So here, I have a factor of x. I'm missing a factor of x minus 2. I'm missing a factor of x plus 1. For b, in order to create a common denominator, I have the factor of x minus 2. I have that already. I'm missing the factor of x and x plus 1. So we have plus b times x and x plus 1. Just the missing factors of your LCD, of your common denominator. Lastly, we got plus c. I'm missing x, and I'm missing x minus 2. Show of hands if you got that far on your own. Good, that's fantastic. That's the whole idea. Now, can you find A, B, and C by plugging in some different numbers?
Yeah.
Hello, can you do that?
Yeah.
Tell me the 3 numbers you'd probably plug in here.
0,
0, for sure. And then what?
-1.
2 would be 1, and then the other one? Yeah, plug those numbers in. If you haven't done it already, go ahead and do that. So when x equals 0, that's nice. Some of your factors are going to go, some of your terms actually, some of your terms are going to go to 0. When x equals 2, some of your terms are going to go to 0. When x equals -1, some of your terms are going to go to 0. Fortunately, man, you got to, this is nice to plug stuff into, right? There's actually a square over there. That's beautiful. I'm going to start working on this for the sake of time, but I want to understand if you guys, I want to know if you guys understand the idea here. So we're checking for numbers that change some of your factors to 0. If your factors change to 0, some of your terms are going to go to 0. So when I plug in 0, start from the left. 0 plus 2 is 2. Okay, if I plug in 0 here, I get -2 and I get 1. So this is A times -2 times 1 plus, well, that's a 0 now. I'm plugging in 0. This goes to 0, this goes to 0. I'm good to go. Now let's plug in 2. If I plug in 2, don't forget you have to actually plug it in here. 2 plus 2 is 4 equals, if I plug in 2, 2 minus 2 is 0, this whole term is gone. 2 minus 2 is 0, this whole term is gone. I get b times 2 times 3. Did you get 2 times 3? B times 2 times 3? Yes. Good. Lastly, if I plug in negative 1, remember to actually plug it in. Negative 1 plus 2 is... If I plug in negative 1 here, this is 0, whole term gone. This is 0, whole term gone. This is not 0. I get C times negative 1, that's what I'm plugging in, times negative 3. Show of hands if you made it that far. Good deal. Now we're almost done here. So, simplify a little bit. 2 equals negative 2a, therefore a equals how much?
Negative 1.
4 equals 6b, therefore b equals how much? Is it okay to get a fraction?
Yes.
Don't worry about it. 1 equals 3c. C equals 1/3. Hey, look at that. Those were the 3 constants I was looking for. A, B, and C. What that means is that our original, actually right here, our original integral changes to this. Please watch very carefully on how I do this. I want to make sure all our signs are correct. You guys are okay to this point, right? Did this make sense to you?
Yes.
Now that we have our A, B, and C, check it out. What I know is that our integral is x. Don't forget about this stuff. Plus 1 minus, I put my big bracket. So this should look identical, x plus 1 minus big bracket. Now inside that big bracket, we just did a partial fraction of this thing. What I know is that the partial fraction of this thing right here equals a over x plus b over x minus 2 plus c over x plus 1. Do I have my a, my b, and my c?
Yep.
Then what this is equal to is negative 1 over x plus, just do the fraction like this. 2/3 over x minus 2. Don't worry about that. Plus 1/3 over x plus 1 dx. A big bracket. Let me double check to make sure you guys are good with it. Do you see how this becomes these 3 fractions?
Yeah.
We found a, b, and c, right? So if we know this is equal to, hey, a plus b plus c over these relative denominators, we got negative 1 over x. Perfect. We got 2/3 over x minus 2. Got it. We got 1/3 over x plus 1. Not a problem. What are we going to do next?
Integrate.
No, we're not going to integrate now. We're going to make sure our signs are correct. So what are we going to do now? We're going to distribute that. So x plus 1 plus 1 over x minus 2/3 over x minus 2 minus 1/3 over x plus 1 dx on the whole thing. Are you ready for the last little part? Yeah? Interesting?
Yes.
Interesting we can actually do it, huh? Kind of weird. But all it is algebra. It's saying it's rational. Break it up into fractions. Not even a big deal. Now that you've broken it up into fractions, these are all easy to do. What's the integral of x? I'm going to write that as 1/2 x squared. You okay with that?
Yes.
What's the integral of 1? What's the integral? Everybody should know this. Integral of 1 over x.
Ln absolute value of x.
Cool. We got this one. We got this one. We got ln absolute value of x. We're going to have a minus sign. Here's how you deal with this. Look at the board here real quick. You keep your constant just like we did in the previous example. So this will be 2. I can write it correctly. I thought it. 2/3. 2/3 comes out front. Remember, if this was an integral by itself, look at, if this was an integral by itself, so integral dx, you'd pull out the 2/3, wouldn't you? You'd have 1 over x minus 2. You do a little substitution. U equals x minus 2. Du equals dx. There's no constant pulling forward. You're good to go. Then you'd resubstitute back in for u equals x minus 2. It's the same idea we've been doing. So 2/3 comes out. We'd have an ln. We'd have an absolute value, x minus 2, close absolute value. It's really you learn some of the basic u substitutions that allows you to do this in your head. Otherwise, we spend forever doing this stuff. So yeah, if you need it, do it. But if you don't, if you can do it like this, that's fine. We've learned enough about this to be okay with that. Minus what?
1/3.
Uh-huh. Are you supposed to forget those absolute values?
No.
Absolutely not. No. And then...
Plus c.
1/2 x squared, x, ln absolute value x. 2/3 comes forward, another ln. 1/3 comes forward, another ln. Show of hands, feel okay with what we've done. Awesome. All right, we're on to our next example. Let's take a look at this integral. Now, of course, the first things we check for this, just like any integral, is does it fit anything we can do that's easy? Does it fit a substitution? Well, of course not. Does it fit integration by parts? No, it doesn't. Trig sub? No, nothing like that. Then we start thinking about, okay, think about this as a rational, as a partial fraction. Is the degree here less than the degree here? Well, that's great. When it wasn't, what do we have to do when it's not? If we do our long division, then it reduces the degree of the numerator, and we go for partial fractions after that. I believe our last example was like that one, right? Okay, so if we don't have something that we have to do long division with, we jump straight into the partial fraction. What's the first step in doing partial fractions? Factoring, yeah, not the numerator, I don't care about that, but denominator for sure. So let's go ahead, let's factor the denominator. Can you factor x cubed plus x squared minus x minus 1?
Yes.
I can. Can you factor it?
Break it into 2 parts.
Ah. What do you do when you have 4 terms? You group them. Try grouping them. Unless you see an obvious factor like, of course, a GCF, like x or a number or something. Yeah, okay, cool. Factor that. But if you don't see that, try factoring by grouping for 4 terms. If that doesn't work, you have to find a root. So you'd have to guess and check for a root or find some other method. There are more advanced ways to factor. I'm not going to teach them here. That's a higher class on how to factor cubics and quartics and to prove that quintics are not factorable. It takes a long time to prove that. But you prove it for 5 and higher. You can't generally factor it. For 4 and lower, you can. There's formulas for it. But for us, to make it easy, you factor a GCF first if you can, like an x if it goes into all the terms. If not, try factoring by grouping. If not, then you have to come up with something that actually works, like a number that gives you 0, and then you can factor out x minus that number. And that's the idea. You can do that by division or synthetic division. So anyhow, for grouping, we'd have our x cubed. I'm going to erase this in a second, so make sure you have this down. Minus x minus 1. Grouping works like this. You group the first 2 terms and you factor out the GCF. You group the last 2 terms and you factor out the GCF. Notice when I factor out -1, it changes my sign. And then you factor this out. And we get x plus 1 and we get x squared minus 1. We okay with that so far?
Yeah.
Now, is this good enough for us? What's the problem with that?
X squared minus 1.
Okay, so when we say factor, we imply factored completely. Factoring means this. Factor means linear and or irreducible quadratics. So if I end right here with x plus 1 and x squared minus 1, this one's great. That's cool. That's linear. Linear means power 1. X to the first power. You with me?
Yeah.
This one, this is quadratic. That would be cool if it was plus. If it's plus, you're done. Do you see why?
Yeah.
You can't factor x squared plus 1. But if it's x squared minus 1, that means you have to keep going. So we do x plus 1, and we do x plus 1, x minus 1. Show of hands feel okay with that one. Now, when you factor something, we do want to make this in simplest form. So what we're going to do, I'm going to write this a little bit backwards. I'm going to write x minus 1. Then I'm going to write x plus 1. Yeah. Listen, I know it's basic algebra, but I want to make sure you're okay with it. Are you okay with factoring by grouping?
Yeah.
Do you understand that we are not going to stop right here with this thing? We're going to factor as much as we possibly can until we get down to linear or irreducible quadratic. Show of hands feel okay with that so far. Then I like to rewrite it as linear factors first. Everyone does this. Linear factors first, and then powers of linear factors, and then irreducible quadratics, and then powers of irreducible quadratics. That's typically the way that we write these. So we've got linear, and then linear to the second power. You guys okay with this so far? So I'm going to change this. I'm going to say, no. This is not good enough. This is actually x minus 1, and then x plus 1 to the second power. Any questions on this before I erase it? So we have factored by grouping, we continue to factor, we grouped our factors that were the same, so x plus 1 we squared. Now this is different. You see, before what we had was we had unique linear factors, remember that? And we set this up as a over x minus 1, and then b over x plus 1, stuff like that. Well, when we have these repeated linear factors, that's actually case number 2. So case 2, is when we have repeated linear factors. Here's what we mean by repeated. It means that you have more than one of them. So for instance, we have x minus 1, we had an x plus 1, and we had another x plus 1. That's why we had this x plus 1 squared. This factor was repeated, hence the square. If it was repeated again, we have to the 3rd power. You guys with me on this one? So here's how you do it. With any repeated linear factors, what we end up doing is we write a1 over the first factor plus a2 over that factor to whatever power we have, and we continue until we run out of the repeated factors. So for instance, if this was to the 5th power, what you'd end up doing, you'd have a1 over whatever linear factor you got, okay? And you'd exhaust those powers of linear factors. I'll show you in a minute how to do that. If we had a to the 5th, you'd have a1 over the factor, a different one, so b. You'd have b over the factor squared, then c over the factor to the 3rd, then d over the factor to the 4th, then e over the factor to the 5th. You have every single different power of that factor. Are you with me on this one? Let me show you how it works here for us. So in our case, what we're going to end up getting is, how many fractions do you think we're going to get here? We're still going to get 3, that's right. So we're still going to have 1, look at this, 2, and again, 3. Do you understand why we have 3 fractions here?
Yes.
We still have those 3 factors initially. We still do. It's just one was repeated. And so what we're going to have, what do you think is going to be my first denominator?
X plus 1.
X minus 1. X minus 1 is going to be there. You guys with me? And then what we do is we say, oh, okay, have we exhausted all the powers of x minus 1?
Yeah.
There's just one of them. We're good. Now we move on to the next one. X plus 1. X plus 1's got to be here. Have we exhausted all the powers of x plus 1?
No.
No. So we go x plus 1.
Square.
Very good. Okay, let's see if you're paying attention. What if this was to the 4th power?
Keep going.
2 more. I'd have x plus 1 to the 3rd, x plus 1 to the 4th. Does that make sense to you? So this one, hey, we're done with that one. This one would be to the 1st, then to the 2nd, then to the 3rd,
Until you get to 4.
until you get all the powers up there, until you exhaust all of them. You with me on that one? Because we have these different factors, if you had this, you'd really have x plus 1, and then another, sorry, x minus 1, then x plus 1, times x plus 1, times x plus 1. You'd have 5 factors there. We show those powers to show those different possibilities of those factors. Now, where did I stop? What was that one?
Square.
2. Okay, good. Now, fortunately for us, they're still linear, right? They're still linear. So all we need on the numerators are A and B and C. And then we do exactly the same thing we did before. So now we have 2 cases. We have the cases where we have distinct linear factors, where we have x minus 1 and it doesn't happen again. We have x plus 1 and it doesn't happen again. That was our first case. In that case, it's pretty straightforward. We just have every different factor on the denominator, A, B, C, D, E, whatever, until you exhaust them. You guys with me on that one? Then, now we have the second case. We've got the case where we might have some repeated linear factors. For those linear factors that aren't repeated, do the same thing. Exactly the same. For those ones that are repeated, have the first power, then have the second power. This is the idea of partial fractions. This is how it works. You guys okay with it? Now, can we make a common denominator still? be smart about it. When I'm making the common denominator, remember the idea is make a common denominator, then ignore the denominator. So ultimately we're going to have 2x squared plus 3x plus 7 equal to whatever I get upon finding my common denominator. Here's the whole deal though. Listen and look. You're going to have, with repeated linears, a lot of the same things, aren't you? Use the largest power here. So when I find my common denominator on this fraction, of course I'm not multiplying by this guy. I already got that guy. But look over here. I need to match this up. I'm not missing the x minus 1. I'm missing the x plus 1 squared. Don't take both of them. Just take the largest power. Does that make sense to you? So I don't need this and this. This one kind of counts for this one as well. This one is the only factor I'm missing. You can see that on this previous fraction. In order to find a common denominator with this, I would just have to multiply by x plus 1 to the third or to the second?
Second.
To the second. So far so good? It's just algebra, but I want to make sure you're good with it. Plus. So we covered up, we take the largest power. That is what's giving us our common denominator. Now we move on to the b. What's missing on this b fraction?
X minus 1.
Okay, x minus 1 is missing. Look, you can look here. If I cover that up, what's missing here? Well, x minus 1 is missing from there. What else is missing from here?
Square.
The squares. Okay, so do I multiply it by x plus 1 squared? Would that be a good idea? No, don't do that. It's way too much. What should I multiply by? You're only missing one factor of the x plus 1. Are you guys getting that? So this, no. So when I look here, yeah, I was missing x plus 1, but more than that, I'm missing x plus 1 squared. That's why we're multiplying by that. So I'm missing this whole factor here. With the b, I've got one factor of x plus 1 already. I'm only missing one more. This, look at this, this would give us the x plus 1 squared, and this would give us the x minus 1. So I'm missing x minus 1 and one factor of x plus 1. From the c, let's look at the c. What am I missing from here to here? What's missing?
X minus 1.
That's it. So I wouldn't take this one. I've already got it. It's like trading cards. You go, I got 2 Jose Cansecos. I got another Jose Canseco. Do you need it? No, I already got 2 of them. I don't need another Jose Canseco. Let's just want to make some money and sell cards, but we already got those. We don't need an extra one. We have enough of our Jose Cansecos. That's a weird analogy, wasn't it? Anyway, question?
So because you already have the x plus 1 squared on the bottom, you only need x minus 1 for c?
That's correct. Basically, we're looking at these fractions, and some people teach it, cover this up, take the rest of it, okay? Not this one, but the largest power. I prefer you to think of, we're finding a common denominator. So look here, look here. What's missing between here and here? X plus 1 to the second power is missing. We need x plus 1 to the second. Look here, look here. What's missing? X minus 1 and one factor of x plus 1. Does that make sense? Look here, look here. What's missing? That's it. Not x plus 1. You already have the x plus 1 squared. Honestly, show of hands if you're okay with that so far. Now, did I teach you the plugging in that cheating way?
Yes.
Is the cheating way going to work for here?
No.
Put 1.
Why not? Can you make this 0?
Yeah.
Of course you can. Can you make this 0?
Yeah.
Can you make this 0?
Yeah.
Can you make this 0? Then why would that work? It works for linears. Works really well for linears. All right. It doesn't work for quadratics. We'll learn about that in a minute. So, why don't you go ahead and do that as I do on the board. See if you can find the correct coefficients of A, B, and C. So, tell me the numbers that you are probably going to be plugging in here.
1 and negative 1.
1 and definitely negative 1. We try those right off the bat because negative 1's going to give us some zeros, 1's going to give us some zeros. We'll be able to find at least 2 of these things. For the last one, I'll teach you how to do that in a minute. So plug it in. Did you already do them? Go for it. I really want you to try it. plugging in 1. If I plug in 1, 1 minus 1 is 0, this is gone. 1 minus 1 is 0, this whole thing's gone. 1 plus 1, that's 2.
Squared.
So all I know is that 12 equals a times 2 squared. Did you guys get that as well?
It's 4a.
I think a is 3. Did you get a is 3?
Yeah.
Awesome. Now, do negative 1. Do the easy ones first. So, negative 1. If I plug in negative 1, what I know is that on this side I get, oh man, what is that? 2 minus 3 plus 7. How much did you get? 6? Okay. So, if I plug in negative 1, negative 1 plus 1 is 0, whole term gone. Negative 1 plus 1 is 0, whole term gone. Negative 1, negative 1 minus 1, how much is that?
Negative 2.
So C times negative 2. What's C equal?
It's negative 3.
Now here's an issue. Did it give you B? So I plugged in the numbers that give me 0. I got A and C, I didn't get B. Here's a little trick. When you get down to here and like, wait a second, with these repeated linears, this happens a lot, okay? Because you're going to have stuff that looks like this, where there's not a number, there's no X, there's no number you can actually plug in. You know what, while I'm thinking of it as well, so let me think of this right now. If I had X to the 3rd power, like this, if I had X to the 3rd, that would count as repeated linears. This is not irreducible quadratic, this is repeated linears. You'd have something over X, plus something over X squared, plus something over X to the 3rd. You'd have a D, an E, and an F. Does that make sense to you?
Mm-hmm.
So X to the 3rd is repeated linears. X, and then X squared, and then X to the 3rd. Okay? Just while it was on my mind, wanted to clear that up. I know some of your problems are like that. So let's say that we don't have a number that gives us 0 for one whole term. Just pick another number to plug in. Something easy. I would plug in probably 0. Just plug in 0. You can plug in any number you want, correct? If I plug in 0, yeah, it's not going to get rid of anything, but it's going to make it easier to do. So I'd plug in x equals 0. Check it. If I plug in x equals 0, what happens on the left-hand side?
7.
If I plug in x equals 0 over here, well, all I'm going to get is a times 1 squared, or a times 1. Then I'm going to get b times, let's plug in 0 here. If I plug in 0, I'm going to get negative 1. I'm going to get positive 1. Plus, if I plug in 0 here, I'm going to get c times negative 1. Ladies and gentlemen, did you follow that? Just pick another easy number to plug in for these linears. It's kind of nice. If I plug in, well, not 1, I already dealt with that. Negative 1, I dealt with that. Those were the easy ones, right? Those give us lots of zeros. Take another number. You plug in anything you want to. You plug in 7, or 12, or negative 15, or 1. Well, you already did it. Or 0. 1 in a different case. But plug in whatever you want. And that way you get, well, an equation. 7 on the left-hand side. Over here we get 7 equals A minus B.
Minus C.
Hey, this is why we did this first. Do you know how much A is?
Yeah.
Do you know how much B is?
Yeah.
B.
No, not B.
Not B.
I
Do
mean,
you know how much C is?
Yeah.
Plug them in and find it. So once you deal with a couple of these factors, the rest of them become pretty darn easy as far as linears go. Oops. So we've got 3 minus b and then plus 3 because we have minus a negative. Looks like we're going to get what?
I got a
Negative 1. Altogether, this would be 6. Subtract the 6, we get 1 equals negative b, or b equals negative 1. Okay, honestly, that's the hard part, finding out the a, b, and the c. At this point, hey, we're ready to split this thing up. Show of hands, feel okay with this so far? So what we know is that our original integral of 2x squared plus 3x plus 7 over x to the 3rd plus x squared minus x minus 1 dx is now equal to a brand new integral. Let's put this thing all together. What we knew is that partial fractions said this can be broken up like this. 1, 2, 3 fractions. What it said was my denominators are x minus 1. That's going to be easy. X plus 1, that's going to be easy. X plus 1 squared. Well, a little different, but not such a big deal. On the numerators, it said that, well, provided you find a common denominator, we did, and can solve for these coefficients, A, B, C, we did, then you know the coefficients of your fractions, or basically the numerators of your fractions. 3, don't get these out of order, okay? 3 from A, and then,
-1.
yeah, -1 goes here. You guys okay with that? And then lastly, it's...
-3.
I'd probably clean this up a little bit. We just want to make sure our numbers are correct, so put them in the same order you did it, okay? So x minus 1, x plus 1, x plus 1 squared. We're going to double check. X minus 1, x plus 1, x plus 1 squared. We want A over x minus 1, so 3 over x minus 1. We want B over x plus 1, so -1 over x plus 1. We want C over x plus 1 squared, -3 over x plus 1 squared. So far, so good? Maybe clean this up because it's kind of ugly looking. So instead of plus negatives, let's make this integral of 3 over x minus 1 minus 1 over x plus 1 minus 3 over x plus 1 quantity squared dx. Let's see if you remember how to do these. Remember how to do this integral? That's not bad at all. What's that going to be?
3 over x.
Absolute value.
Sure. This is u sub we do in our head. The derivative of x plus 1 is simply 1, so dx equals du, no big deal. So this would be a constant, 3 ln x plus 1 in absolute value. So far so good? Yeah. Minus what?
ln of the absolute value of x plus 1.
Very good. So no problem, no problem. Is this also an ln? Is this also an ln? Be careful. This is not an ln. ln is a quantity to the first power. This one, maybe think of this as a different integral. Maybe pull that 3 out, pull this x plus 1 to the -2.
So -3.
If you were given this in Calculus 1, you'd be able to do it. This is actually pretty easy. You can, I don't know if they teach you, yeah, they teach you substitution in Calculus 1, don't they?
Yeah.
You'd be able to do this just fine. Don't forget the stuff you know. Don't make it harder than it is. Don't be throwing ln's all over the place when it's not an ln. This is, hey, that's a power. That's a -2. So when we do this, we have 3 because of our constant. We'd have x plus 1 to the -1 because you add, and then you divide by -1 because you divide by your new exponent. What that would become is -3 over x plus 1. I want to verify that you guys are okay with this. This would be -3 over x plus 1. Yes, no? You sure? Okay, so notice how we took this piece away. So I have minus that piece, -3 over x plus 1. Clean it up just a little bit. We'll have 3 ln absolute value x minus 1 minus ln absolute value x plus 1 plus 3 over x plus 1. And finally, let me know I'm done. Oh, kind of. I'm going to show you one more thing with this. Here's what I want to know. Are you guys okay with the algebra of getting our partial fractions? Yes, no? Are you okay with integral of this guy? And this one? How about that one? That should really be okay, right? Because we're used to this. Bring up that exponent. Sure, no problem. X plus 1 to -2. You do a little u substitution, but it's just x plus 1. No big deal. If this was like 2x plus 1, you'd have a 1/2. Are you with me? So here, I mean, no problem. I know I'm doing it in my head. I get it. I'm not supposed to, maybe. But it's a straight substitution. So we have a u to the -1. We have -3 over u. Then we'd have -3 over x plus 1. You resubstitute that right back in there. Since we're subtracting a negative, we change it to a plus. Add a plus c on there. Now, one little thing I want to talk about. Occasionally, you're going to do some problems that look different when you're doing these repeated linear factors or even linear factors. Because what happens is you get a lot of ln's being added and subtracted, and with coefficients out front. Now, what we know from our chapter 6 work with with exponentials and logarithms, is that these really mean exponents. this really means a division. So occasionally you'll get stuff like this. You say, okay, well this can translate to, just to make it nicer looking, ln of x minus 1 to the third over x plus 1 in absolute value plus 3 over x plus 1 plus c. Your exponent, this is how you would do this in order. Your exponent would move up. It would become an exponent on x minus 1. Subtracting two ln's is a division problem. Notice the cube does not go to both. It goes just to this first one, your numerator. Are you okay with that one? Can't really do much with this one, so you leave it. But that's another way you can see the answer here. We sure we're okay with that? How do you feel all right with that one? You guys ready to move on a little bit? Are there any questions, comments, or concerns? Am I making this straightforward enough for you guys to understand it? Okay, well, there's a couple other cases that we got to master, so let's continue moving on. Most of these are going to take us at least one space of the board, so if there's any questions I need to know now, because I'm going to erase most of it. You got it? All that nice work. Here we go. Oh my. Okay. Well, that looks fun. Let's go ahead and do that one. Let's run through the whole process of solving integrals, all right? Because on your test that I'm going to give you, I'm not going to tell you what to do. You're going to look at it and go, oh, yeah, okay, I know what to do here. So let's pretend this is a test situation. You look at this problem and go ahead and do it. And you go, what do you check for first?
For the denominators, you got the higher power.
I would check for substitution. Honestly, that's what I would check for. Is this the derivative of this thing, disregarding constants? It's not. But I'd check that first, because if it is, that's an easy problem. That's really, really fast. You with me? I'd check it first. After that, you go, okay, well, does it look like anything we've had before? Anything like a integration by parts?
No.
It's not a product. Those are typically products. Does it have any trigonometry in it? Any square roots or something we can turn into trigonometry? Any completing the square? No, it's a cubic. Partial fractions? Yeah, looks like a partial fraction to me. Okay, something we could use partial fractions for. The first thing we check, I think you guys said it first, what do we check?
The degree.
Yeah, degree on the numerator has to be less than the degree on the denominator, or you do what with it? Yeah, and that reduces the degree of the numerator for you. So that's great. So here, we're good to go. No long division necessary, thankfully. Okay, now that we've determined that we're going to do partial fractions, what's your first step? Break it, factor it. Yeah, we're going to factor it. And we're going to factor by, Aaron said we're going to factor by grouping. Why don't you try factoring by grouping? Go for it. I'm wondering if you get the same thing I did. Did you get 2x minus 1, and then did you get x squared minus 4?
Yeah, plus 4.
Oh, good. I was testing you. You passed. Did you get a plus 4? If you got, let me have your eyes on the board here real quick. You guys okay with the grouping? By the way, you'll notice what I'm writing is the linears first. Do you see that? Now, if you had an x squared minus 4, would you stop right here? If you have an x squared plus 4, do you continue going? Can you factor x squared plus 4? If you start factoring this as x minus 2x plus 2, your problem's going down the poo-poo hole. All right, that's not good. We can't start factoring like we don't know what we're doing here. So this is your first case of an irreducible quadratic. That's this next case right here. Case number 3 is when you have irreducible quadratics. Irreducible quadratics. So we've factored by grouping, it worked. We had 2x minus 1, no problem. Our remaining factor is x squared plus 4. This one, okay, what is this? Is this a quadratic or is this a
Linear.
linears? You're automatically done. There's no more factoring in that. You're done. Is this a linear or quadratic?
Quadratic.
Can you reduce it more? Then it stays an irreducible quadratic. For irreducible quadratics, what we do, we write the irreducible quadratic if we have powers, we'd write it again and again. So we write the first irreducible quadratic, and then the second irreducible quadratic. 2, 2, 2. And then the third one, and so on until we exhaust all of our irreducible quadratics. And on the numerators, hopefully this makes sense to you. Whatever factor you have, your numerator should be 1 degree lower than that. So for linears, 1 degree lower than a linear is a constant. 1 degree lower than a quadratic is a linear. So for linears, we'd have, that's what we had here. We had A, we had B, we had C. 1 degree lower. Does that make sense to you? For our linears. For quadratics, we're going to have linears. AX plus B. CX plus D. And so on, and so forth, and so on, and so forth. This is the idea here. Show of hands feel okay with that one. Now let's put that into practice with our problem here. So notice how our cases are kind of, they're building, right? We're building on what we already know. So if you have a linear and you have an irreducible quadratic, you can do 2 different things in the same problem. How many fractions are we going to have here? What do you think? Are there any factors to a power?
No.
Okay, so this is one factor, this is another factor. Are they repeated?
No.
Okay, that's our next case, okay, is when you actually repeat these. So, is this repeated? That's just one factor. Is this repeated? That's just one factor. You can't reduce it, right? So it's irreducible quadratic. That means you're going to have 2 fractions. Okay, tell me, folks, what's going to be on my first denominator?
2x minus 1.
Is that linear or quadratic? I know I've asked it, but is it linear or quadratic? Okay. What's on my next fraction?
X squared plus 4.
Is that linear or quadratic?
Quadratic.
And it's irreducible. Remember, you've got to make sure that you have simplified this or factored this as much as possible. Show of hands if you're okay with this so far. It's the same idea. You have a number of factors, make a fraction for each factor. That's it. Now, on the numerators, it's important you get this right, get it correct. For every linear, we put a constant. For every quadratic, we put a linear, 1 degree lower than what we have. We do that for every single fraction. Typically, this is why I write my linears first and then my quadratics so I don't lose any. Okay, so I don't have to go back and forth. So here, what's going to be here?
A.
That's right. What do I want to do in AX plus B?
No.
No, it's linear. I want a constant for linears. How about this one? Do I put a, just a B?
Bx plus c.
Good. What I want is a linear for a quadratic. So, constants for our linears. That's what we've been doing here, folks. That's what this is. Then a linear for my quadratic. So notice how the degree is 1 lower. This is x to the first, this is x to the 0. This is x to the second, this is x to the first. It's 1 degree lower. That's the whole idea. Should fans feel okay with that one? Then you're good to go. That's it. Same stuff after this. So why don't you guys go ahead and tell me what I would do to get a common denominator on my first fraction. What's the missing factor here? Remember the way I do it? I look here, and I look here. What's missing from here to here?
X squared plus 4.
So I have a and x squared plus 4. Plus. I look here, and I look here. What's missing from here to here?
2x minus 1.
So the way this looks is bx plus c. Remember, it's the whole numerator. I'm sorry, what's missing there?
2x minus 1.
So again, for the last time, hopefully, when we find a common denominator, we multiply by the missing factors on both the numerator and denominator. We do. The missing factors are x squared plus 4. We have this one. We're missing x squared plus 4. So that's why we got our a times x squared plus 4. Here we're missing the 2x minus 1. We already got this. We're missing the 2x minus 1. That goes here and here. As soon as we get that common denominator, we ignore it. We just set the numerators equal to each other. So this numerator equals this new numerator. This would be the numerator. You follow? Just keep in mind, it's a times this one, this x squared minus 4, and then it's this whole bx plus c times the 2x minus 1. Show of hands if you're okay with that one. Now, this is what I was talking about as far as sometimes you can cheat and sometimes you can't. Right now, it's going to be pretty difficult to cheat at this thing and plug in a number that's going to work. And the reason why it's going to be a little difficult to cheat is because if we plug in stuff like, oh, I don't know, a number to make this 0, we'd have to come up with 1/2. 1/2 is going to be difficult to plug in here, and difficult to plug in here, and difficult to plug in over there. Okay, you can try it. You can plug in things like 0 if you want. So 0 would give you -1 times c, and it would give you 4a. So and it give you equals -21, but it's not going to eliminate everything. All right. So sometimes one of the easier ways to go is just to distribute and actually see what happens. So that's what I want you to do right here. If you want to plug in some numbers, and sometimes you get lucky, do it. That's what I would try every time. If there's an easy number to plug in, man, do it. But if there's not, sometimes you're left with actually distributing, combine your terms, and going forward. So go ahead and do that now. Distribute, combine your terms. I'm going to do it while you guys are doing it. Make sure I got that. X squared plus 4x. 2bx squared minus bx plus 2cx. Did you get the same thing?
Yes.
Collect your terms. I see a couple x squareds. So I'm going to have a plus 2b x squared. Collect some x's. Again, how I do this, I always put a plus, makes it easier for our signs. When we factor, we'll have -b plus 2c x. Are you guys seeing what I'm talking about there? We put our plus and then we collect our signs inside of our parentheses, -b and 2c. Lastly, we have plus 4a minus c as our constant. We got those ones. Did you make it that far on your own? Fantastic. What's nice about this is when we collect our terms, we have x squared. Hey, we match it up over here. We've got x, we match it up over here with our coefficients. We've got a constant, we match up with our constant. So you tell me, hopefully you can figure this out, if I put a plus 2b, how much is that equal to?
1.
Well, where are you getting that 1 from? This is the coefficient of x squared, isn't it?
Mm-hmm.
This is the coefficient of x squared, isn't it? It's got to be equal. So 1 equals a plus 2b. Let's do the next one. If I put -b plus 2c, -b plus 2c, how much does -b plus 2c have to equal here?
-1.
Since this is the coefficient of x, and this is the coefficient of x, you're right. Now if I put 4a minus c, how much does 4a minus c have to equal? The reason why we use pluses here, it keeps our signs correct. That way you just look here and here and here and set them equal to the coefficients themselves. So this has got to be -21. Show of hands if you're okay with that one so far. Okay, now, you can solve this in a variety of ways. The best way I think I found to solve this, I would probably do a substitution. I'd probably set this one. I'm going to do a lot of math quickly in my head because I don't want to spend a whole lot of time teaching you algebra, okay? So what I would do is I would add the c, add the 21. I would get c equals 4a plus 21. Does that make sense? I would do a substitution here. I'd get negative b plus 2 times 4a plus 21. My equals negative 1. The idea being, if I can get a's and b's, I can combine it with this a's and b's and create a system of equations, and that will let me solve it algebraically. So do our substitution, no problem. We got negative b, cool. 2, no problem. 4a plus 21, that's our c, equals negative 1. Let's do a little distribution. So negative b plus 8a plus 42 equals negative 1. Are you still with me, folks? Okay, now, I'm going to get my a's and b's on one side. I'm going to get my constants on the other side, because that's how this one looks. I'll probably write my 8a first, because that's how this one looks. My minus b equals negative 43. You still okay with that?
Yeah.
This is what we have now. A plus 2b equals 1, 8a minus b equals negative 43. You guys should know how to do systems of equations in one of two ways. Either you do a substitution, which would work here just fine, or you do elimination, which is what I'm going to do here, and that's going to work just fine. So if I did elimination, I'd multiply this by,
2.
I'd multiply it by 2. So if I multiply by 2, we get a plus 2b equals 1. We get 16a minus 2b equals negative 86. If I've done that right. Have I done that right? Yes. Then what do we do? In this case, we add. We get 17a. This is gone equals negative 85. Man, this is kind of nice now. Let's solve it. How much is a?
Negative 85 over 17.
Negative 85 over 17. What is it?
5.
5.
5.
Negative.
I'm just telling what you give me. What is it?
Negative.
Oh, okay. Does it matter? It doesn't matter, right? I mean,
It
matters.
it doesn't matter. From here, can you solve the rest of them?
Yes.
Piece of cake. If a is negative 5, then
Solve for C.
solve for all.
Solve for B.
Solve for whatever you want. You can solve for C by this one. By this one actually would be nice. You could solve for B by this one. That's what I would do first. So if I plug in negative 5 here, I'd be adding that and dividing by 2. B is how much?
3.
Sure, negative 5 plus 2b equals 1. Therefore, b equals 3. So I got this one, and I got this one now. Working over here, I do this for our C. If I plug in negative 5 there, hey, look at that. 4 times negative 5 is negative 20. Negative 20 plus 21 is 1. 1. That was relatively painless. Not so bad, right? Not as easy as plugging numbers in, but not horribly bad. Hey, now that we have our coefficients, can we rewrite our integral? I know we've done a lot of algebra, okay, but I'm going to come right back to here. So our integral x squared minus x minus 21 over 2x to the third minus x squared plus 8x minus 4, dear goodness me, equals an integral of 2 fractions now. Notice we have three coefficients, we have 3 constants, but we don't have 3 fractions. We have 2 fractions. The first fraction is over what, please? No, the first fraction is over what?
2x minus 1.
1.
The second fraction is over
X squared plus 4.
dx. On the numerator of our first fraction, it says that we're supposed to have only an a. What goes here?
Negative 5.
On the numerator of our second fraction, we're supposed to have a bx plus c.
3x plus 1.
Beautiful. We knew that this fraction can be broken up. We just showed it. We know that a is -5, -5 over 2x minus 1. We know that b is 3, we just showed it. We know that c is 1, plug those numbers in, we get 3x plus 1 over x squared plus 4. Should finish feel okay with that one. Now, I've got to erase this stuff. Do you have any questions so far on this? Are you sure? Okay. This, very straightforward. Very straightforward. This is going to be an ln. Do you guys see it?
Yeah.
Linear ln. The only difference is this is not going to be -5 ln absolute value 2x minus 1. It's going to be -5 ln absolute value 2x minus 1 over 2. Do you see where the over 2 is going to come from? It's a little u sub right here. If u equals 2x minus 1, du equals 2 dx, or du over 2 equals dx. The over 2 is from right there. Does that make sense to you?
Yeah.
I do those in my head. If you need to show your work, you show your work. Don't get those wrong. Now I'm going to show that to you in a little bit. This one, some of you guys are struggling with concepts like this. You're like, man, how in the crap am I going to do? What am I going to do there? Think back to what fractions are made up of. Fractions can always be split up. Always. Now let's think it through, okay? Think it through. What would you do here? Basic u sub. Or just do it in your head. Look at this one. What would you do here? That's a u sub. What's the derivative of an x squared?
2x.
I don't care about the constant. It's going to be an x. Do you guys see what I'm talking about? How about that one? Let's think about that one. Okay, we're going to do this over here. Do you guys want to finish this problem today?
Yes.
Okay, it's going to take us about 3 minutes. Did you have questions on that? Too late. Okay, let's just run down there. I'm going to split these up because we're going to, this is crazy, but we're going to use 3 different techniques on each of these 3 integrals. So to show this accurately in mathematics, you don't want to just do this all as one, okay? Because you have 2 different substitutions here. Are you following me? So you're going to, actually 3. You're going to split this up into 3 different pieces. So integral of the first one, plus integral of the second one, plus integral of the third one. You could have pulled out the -5 as well. This integral is fairly straightforward. Our u equals 2x minus 1. Our du equals 2 dx. Our du over 2 equals dx. Therefore, when you do your integral, we get -5 halves. 5 halves. ln absolute value of 2x minus 1. And absolute value. I need to show if you feel okay with that one. This would be -5 over u. That would be -5 ln absolute value u. You plug back in for your u, and the du over 2 gives us our 5 halves. So -5 halves over u ln u. Okay with that one? No, we're going quick, but if you need a refresher on that, go back and look at that section online, or on the video. On the line. Okay, next one. Don't let these things escape you like this. If you're stuck, you go, man, I can't do that one. Try splitting it up. Then it makes a really easy integral doable for hard integral doable for you. Makes it easier. Do a basic u sub. Here, u equals x squared plus 4. Du equals 2 dx. Du over 2 equals x dx. There it is. Right there. That means that we have 3 integral 1 over u du over 2. Are we okay with that one?
Yeah.
Okay, well that means that we're going to have 3/2 ln absolute value u. So this will be plus, use purple here to show that, same thing, plus 3/2 absolute value, ln absolute value of what goes in there? And absolute value. I want to make sure you guys are golden on this stuff. You guys okay with the first one? -5, got a little substitution, that's where the over 2 comes from. Here, basic substitution, all basic. du equals 2 dx, du over 2 equals x dx. This is du over 2. Therefore, we're going to have a 3/2. That's the over 2. We're going to have integral of 1 over u. So we're having 3/2 ln absolute value u. Plug in back for the u. U is x squared plus 4. We got our integral. Am I explaining this well enough for you guys? Okay, next up. You can actually do this 2 ways. I'm going to show you a very cool idea here that you're going to be using. One idea is you understand that I could make this 1 over, I could force this to factor as x over 2 squared plus 1 times 4. That would be 1/4 the integral of 1 over x plus over 2 squared plus 1. And then you realize that's tan inverse. And you go, oh, look at that. That's tan inverse x over 2 1/2, because you have a little u sub there. You can do it that way. If you didn't catch that, don't worry about it so much. I'll show you a different way. Hope that's right, by the way. We'll see. My constant might be up there. I did it real fast. Here's another option. This almost looks like a trig sub. Do you see it?
Yeah.
What's missing?
Square root.
Ignore it. Ignore the missing square root. If you were to write it as a square root, that would be the hypotenuse. Missing the square root. Did you get that? You can still do,
No, that's a secant.
that's a tangent. You can still do the 2 missing sides. Do you follow that? If you do the 2 missing sides, this would give you the x, this would give you the 2. You can still do the substitution. Tan theta equals x over 2. So who cares if it doesn't have a square root? You can still do this, no problem. This is x, this is 2. Therefore, this is square root of x squared plus 4. Okay. Then x equals tan theta times 2. dx would equal 2 secant squared theta d theta. Our integral would equal 1 over 2 tan theta squared plus 4. Our dx would equal 2 secant squared theta d theta. 2 secant squared theta d theta. I know I just went really fast on this. Are you following that one? You sure? The triangle is the hardest part, right? Then we do, hey, tan theta equals x over 2. No problem. X equals 2 tan theta. Dx equals 2 secant squared theta d theta. Make our substitution. 1 over 2 tan theta squared plus 4. Dx is 2 secant squared theta d theta. That means that our integral becomes 4 tan squared theta plus 4. 2 secant squared theta d theta. Factor the 4 out. If I factor the 4, notice it's even easier. There's no square root here. If we factor the 4, we get 2 secant squared theta d theta over 4 tan squared theta plus 1. Do we follow that?
Yeah.
Hey, look at that. Do you see 1/2? Told you it was a 1/2. That's because of those constants. Hey, 1/2. Integral. Hey, how much is this?
Secant squared theta.
So we're going to have secant squared theta over secant squared theta. That's equal to 1/2 integral. Oh my gosh. This is secant squared theta, right? This is secant squared theta, right? This is 1/2 secant squared theta of what? D theta. Can you integrate 1?
You got it.
Theta.
1 theta.
I'm gonna plug theta. So.
So this is 1/2 theta. Oh, goodness gracious. Here's the whole banana. Is that even a term? Is that a thing?
You just made it a thing.
It's a thing. Whatever. If tan theta equals x over 2, this is if and only if theta equals tan, oh my goodness. This is where all your inverse integrals came from. Booyah.
You just proved it.
Then this is the same thing as 1/2. Tan theta equals x over 2, correct?
Yeah.
Theta equals tan inverse of x over 2. So 1/2
What the hell?
tan inverse x over 2. I believe I had that on the board just a little while ago.
Yeah.
So if you know how to factor that,
Let's see.
you could do it with just your inverse trig function as far as your integrals go. So one last little piece. We're going to add this up here. Don't forget this is our first part. We have plus 1/2 tan inverse x over 2 plus c.
Oh, yeah, that's
Woo.
Now my question is, did you understand it?
Yes.
Somewhat.
So this one ln, this one's substitution then ln. This one you can do it two ways. You can draw the triangle. This still works. Don't even have to worry about the square root, okay? Just make the triangle accordingly. Or you could have made this factor out the 4. Make it factor the 4. You'd get an x over 2 squared plus 1, and then a 1/4 outside. Do a little substitution for x over 2, and you have an inverse tangent. And that's the idea. Should we feel okay with this one? Okay, so before we get on to our last, thankfully our last example of partial fractions, I covered an example that had this little piece in it, and I want to go over this a little bit more slowly on how you, there's two ways to actually do this, how you can go about doing this problem in one of two different ways. Now the first way is an idea that we get from trigonometric substitution. It's, well, you know what, that looks almost like a triangle, almost like one hypotenuse of a right triangle. You can actually do that. So you could make a right triangle out of this. And the way you can think about it is, well, if this were to have a square root around it like that, this would be the hypotenuse. Does that make sense to you?
Mm-hmm.
So it would be like this. If that were the hypotenuse, well, the other two dimensions here are the sides, or the legs. Well, we would have x and what?
2.
X and 2. Where would the x go?
That one.
This one, yeah, because what we want to do here is make up our tangent relationship. So we'd have x, we'd have 2, and we'd have tan theta equals x over 2, or x equals 2 tan theta. And then, of course, we take our derivative. We have dx equals 2 secant squared theta d theta. You guys okay with that so far?
Mm-hmm.
If you really think about it, you can do this lots of times. Let's consider this one more time. If you had just 1 over x squared plus 4, someone made a comment earlier, well, maybe we can manipulate this a little bit so it's easier to see. Check it out. If I have x, do you understand that it's almost the same thing? It's not the same thing. It's almost the same thing as the square root of x squared.
Mhm.
This is almost true. It's not true because we'd square it, so our negative x's don't really work that way. It's really it's really an absolute value type of idea, but we can use it for here. Especially since we have both positive, we don't have to worry about that. There's no way we can get a negative out of this anyway. So it's going to be positive no matter what. Does that make sense to you? So whether x is positive or negative, we get a positive out of it. We won't have to worry about that scenario. So in our case, we'd say, all right, well, if you want to make this a little bit more understandable about why this can fit a right triangle, here it is. Why this can fit a right triangle is that we could make this the square root of x squared plus 4 squared. Now, for those of you who didn't see it before, do you guys see what I'm talking about? That is a hypotenuse right there. It's just now we have it squared. You follow me? You can do that, no problem. We have our x, we'd have our 2, we'd have, hey, that's my hypotenuse. Now either way you go about doing this, you're going to get the same thing, because when we plug this in, when we do our actual substitution, well, we've got 1. I'll leave it this way, just so you see what I'm talking about. We'd have 1, we'd have something being squared. You with me? Inside here we'd have a square root. We would have 2 tan theta squared plus 4. And then we'd have our dx becomes 2 secant squared theta d theta. You guys get me so far? Now look what happens with the square root and the square. Now, we didn't have to do this. Me personally, I would have gone straight to my triangle from right here. I wouldn't have needed that because I'm used to it. But if you need this, you go, okay, well, this is the same thing as something with a square root squared. Yeah, that's true. That will allow you to see the triangle a little bit more easily, let you set up this relationship on a triangle, let you find tan theta equals x over 2, no big deal. But now watch it. What happens when you square a square root?
Takes it away.
It goes right back to what you had. Does that make sense? So you really didn't need to do it, but you can do it if it helps you see it. So in either case, what we end up getting, and I know that I did this earlier in class, but we'll do it again. We get 2 secant squared theta d theta over, what happens here is we're going to get, I'm going to do a lot of math in my head right now, just so you, hopefully you're with me here. The square and the square root are gone. You follow?
Mm-hmm.
I'd pull out the 4. I take a square root of 4, I'm going to get 2. I'd have a square root. I'm sorry, I wouldn't have a square root anymore. The square root's gone. I made a mistake. This is why I don't like to do the square root, because it's gone now. So maybe I can write this and you guys can follow me from here. We'd pull out the 4, and we'd have secant squared theta. Shoot. I'm going too fast for my own good, aren't I? There we go. That's gone, we pull the 4 out. Of course, we square the 2, we square the tangent. Pull the 4 out. After this, we'd have a 1/2. We'd have a secant squared theta. This becomes secant squared theta, d theta. This is 1/2 the integral of theta. Again, I'm going too fast. I'm doing the integrals in my head. 1 d theta. You don't even need the 1. What's the integral of 1? I went fast. Are you guys okay with getting down that far?
Yeah.
What's the integral of 1?
Theta.
Yeah, in this case it's theta. So 1/2 theta. Can I leave it in terms of theta?
No.
No, but here it is. If tan theta equals x over 2, this happens if and only if theta equals tan inverse of x over 2. Did you guys buy into that one?
Yep.
Tan theta equals x over 2? Hey, theta equals tan inverse of x over 2. So what we get out of this substitution is that our integral is 1/2 tan inverse x over 2 plus c. This would be the long way of doing things, but it is a way. Show of hands if you feel okay with the a way of doing it. You could do a trig sub just by looking here. You can make it fit more of the trig sub idea. Or you could do this. Here's way number 2. Way number 2 is to try to fit this to an integration table. To try to fit this into an integration table just the way it is. And the way it is would be, well, if I can fit this to u squared plus 1 du, the integral of 1 over u squared plus 1 du is tan inverse of u. Plus c, of course. Well, here's another idea then. Instead of going through the whole trig sub idea, well, maybe we just think of, instead of 1 over x squared plus 4 dx, we force this thing to factor out a 4 here. So we could say, okay, well, if I'm trying to make this a 1, I've got to factor out a 4. You get me? Then I'd have 4, and I'd end up getting inside my bracket x squared over 4 plus 1 dx. Do you guys follow the algebra on that? If you don't, just distribute right now, and you'll see that this goes to x squared, and this goes to plus 4. Do you follow? Then what I need to do to fit this format, I need to make this as something squared. So x squared over 4? No. I'm going to pull the 1/4 out. I would have 1 over x over 2 squared plus 1. Does that make sense to you? So instead of x squared over, no, let's think of this something squared. Let's do x over 2 squared. You'll notice that 1/4 is outside, out front. This becomes x over 2 squared. That's still x squared over 4, and then the plus 1. So far, so good? Now you do just a basic u substitution. Basic. So the u equals x over 2, du equals 1/2 dx, 2 du equals dx, and what we end up getting is 1/4 the integral 1 over, what's the x over 2 become?
U.
Yeah, u squared plus 1, and then we have 2 du. So instead of dx, we get our 2 du. Tell me next thing I'm going to do. Pull out the 2. So I get 1/2, 1/4 and 2. The integral of 1 over u squared plus 1 du. Hey, do I know what the integral of 1 over u squared plus 1 is?
Tan inverse of u.
Tan inverse of u. So this becomes 1/2 tan inverse of u. How much is u?
X over 2.
Let's see. Ends up being exactly the same thing. So if you ever see, and you are going to get this a lot, listen, you're going to get this a lot. One of these things where you have 1 over x squared plus 4 or plus 9 or plus 1. If you see that, how many ways can you go about doing it? And either way is fine. If you want the quick way and you want to do just a little substitution, do this. If you like the triangle method, do this. Do I care? I don't care. So as long as you can do one of these ways, I'd say do both of them. Sometimes this is going to be nicer because if I do this, like that, you can still do it. Here, you can't. If I do this, this is not this. No, don't do that. Okay. So then you'd have to do something like along these lines. Show of hands feel okay with this one. Okay, now that was a little bit slower, but I just want to give you a heads up on what you can and can't do with this problem. Did I explain it well enough for you guys to understand it? Okay. Can we go on to our last example?
Yes.
Last one. Let's do it. I'm glad you said yes. I was going to anyway, but now that I have your approval, feel much more better. By the way, were there any questions on this? Too late.
We've done this stuff earlier in chapter 6, right?
We did this stuff earlier in chapter 7, as far as the
7.1.
trig sub. We also did, yeah, we've done all sorts of stuff in chapter 7. So somewhere along the lines, we did this. Yes. You guys got plenty of paper today, right?
Whole notebook full.
Paper? I hope you have a notebook full. This is going to take a few pages of paper for you.
Just start a new page and
Wait, this is one example.
Maybe start a new page. I'm going to need at least 2 of these boards
Thanks for the heads.
for this, so heads up.
just see the notes in next
It's going to take at least a gig or 2 of video, at least. Probably Probably
For
2
this
gigs.
example?
this example.
2
Oh my
gigs.
gosh.
It's this much. See, this and this.
Good thing you have
That's
unlimited
one.
data.
That's nothing compared to grad school, so.
Don't worry, you're going to know how to do all of it. It's not hard. It just takes a lot of,
Steps.
yeah, a lot of steps. No long division, because I'm a nice guy today.
We'll see who agrees.
One division, it's not that bad.
I like long division.
Okay, so let's take a look at our example here. Let's see what exactly is going on. Remember that we have had 3 cases so far, haven't we?
Yes.
Our first case was the easiest one. You get a lot of ln's. It's just it's linear factors. The denominator is all linear factors, like x plus 1, 2x minus 3. Those are linear. And the next case after that, case 2, was you have linear, but then you might have repeated linear. And remember building up on the repeated linear? You do for every power until you reach the highest power. So a over whatever, b over whatever, c over whatever, and you build that up. Now, when we got to quadratics, irreducible quadratics, we no longer had just a constant numerator. We had did I tell you this? It's always 1 degree lower than what your factor is. So for linear, we have constants. For quadratics, we have linears. That's what our numerators are. Well, this last case is not just linear. By the way, can you tell me what the linear factor is here? Whatever that is, turn it off now. Can you tell me what the linear factor is? Yeah, that's linear. We're going to have a over x right now. You with me?
Mm-hmm.
So we don't just neglect our previous knowledge of, hey, what do you do with linear? You're kind of building on them. So you can have more than one case in each example. So linear, sure. Now, do we have any irreducible quadratics up here?
X squared plus 1.
Yeah, that's an irreducible quadratic. Can you factor that?
No.
That's irreducible. But we also have it repeated to a power. And this is our case 4. Case 4 is repeated quadratics. So we had linears, then we had repeated linears. Then we had irreducible quadratics, now we have repeated irreducible quadratics. So this is our case 4.
You forgot the dx.
I wasn't done yet. So now that we're ready to go on our example, let's see what happens when we do this. Now, before we go and do this, I want to give you an example we're definitely not going to go through this whole thing, all right? I want to see if you understand how to build your partial fractions from this. So a little sidestep, okay? Let's say that I had not even an integral, just this thing right here. If I gave you that, would you know how to write the partial fractions to it? This has every case that I can imagine here. So I think it's kind of nice for us to go through this just so you see what's actually going on. Are you guys with me on that one?
Yeah.
First thing you check for is, can you factor your denominators any more? Can I factor this anymore?
No.
This.
Yes.
Factor, not distribute, factor. Factor.
No.
Factor.
No.
No. So these are all non-factorable. Do you believe me?
Yes.
Okay, so they're completely factored. Now, when we go through this, you need to be good at identifying what linear factors are, what repeated linear factors are, what irreducible quadratics are, and what repeated irreducible quadratics are. The same method we use for repeated linear is the same thing we're going to do for repeated irreducible quadratics. Same basic idea. So, when we go through this, oh yeah, you know what the next thing we talked about? You got to check the degree. So how in the world do you check the degree here? What's the degree of the numerator?
4.
What's the degree of the denominator?
3.
A lot more than
A lot more than that. A lot more. Because degree is after you've distributed everything, right? So let's start here. You'd get an x to the 4th somewhere here, wouldn't you?
Yeah.
And you get an x to the 6th. Then you get another x squared. So you have x to the 8th, x to the 9th. Basically, you'd have an x, you'd have an x to the 9th somewhere up here. Do you follow? So naturally, our degree here is less than the degree on a numerator. So degree of denominator is, did I say that backwards?
Yeah.
Degree of numerator is less than degree of denominator. And that's what we're looking for. Thank goodness, because if it wasn't, what would we have to do here?
Combine it.
You'd have to distribute it and then do long division with it, and then the factoring would be crazy again after that. But anyway, this would be the idea. Should of hands feel okay with the idea. Now, let's see if you're good at telling me how many fractions we're going to get. Don't say it out loud. I want you to count them up, how many fractions you're going to get, okay? Don't say it out loud. Everyone do this. How many fractions we're going to get? Have you counted?
Letters or fractions?
Fractions. How many fractions we're going to get?
4, 6,
6.
Let's see. Do you remember what to do with our factors here? Let's see.
Linear.
What's the first one going to be?
A over X.
And then I'm going to have another one with
X minus 1.
Oh, so with repeated, remember this?
Yeah.
When they're by themselves, no problem. When they're repeated, you put the first power, correctly.
It's okay.
Put the first power, then you put
X minus 1 squared.
until you build up to the greatest power here. So here we have x, we have x minus 1, we have x minus 1 squared. That's what repeated linear was. Do you remember that?
Mm-hmm.
Let's just work on all the fractions right now, then we'll fill out the numerators. What's next?
X squared plus 1.
You go to your next one. So our quadratics, so x squared plus 1. That one's not repeated, so I'm good to go. After that, what?
X squared plus X plus 1.
The same thing we did with our repeated linear. So here we had x minus 1. Then we had x minus 1 squared. You take every power up to the largest power. So here, x, no problem. X minus 1 squared, well, you got to have an x minus 1. Then you got to have an x minus 1 squared. X squared plus 1, no problem. That's not to a power, so we just have one of those factors. Here, this is repeated. So I have x squared plus x plus 1. But then I'm going to have another one because it's repeated. You have to go to the largest power that you have. And x squared plus x plus 1 squared. 1, 2, 3, 4, 5, 6. If those people said 6, you're right on the money. If you didn't say 6, do you understand why we get 6 now? You sure? Okay, so we got this, hey, repeated. You're going to have 2 of these. That's what it says, 2. 1, 2 of these. So 1, 2, 3, 4, 5, 6. Just count the powers up. That should be how many fractions you actually get here. So far, so good? Okay. Especially if I would have something like this. A lot of people screw this up. A lot of people do this, and they do that. Is that the appropriate thing to do?
No.
You'd have an x, and then you'd have an x squared. So if you count the powers, 1, 2, 3, 4, 5, 6, 7, this would give you those 7 fractions that you should have on this example. You okay with that one?
Mm-hmm.
Now, let's go ahead. I'm going to erase that again. Let's figure out what we should have. What's the first letter we would start with?
A.
It's linear. Next one.
B.
Good. How about?
C.
This would be C. Yes, that's still C because it's repeated linear.
DX plus E.
Every time we get a quadratic, we have a power degree less. So power 1, this is repeated linear, it counts towards linear, so we have a C, we have dx plus E, we have
FX plus G.
quadratic,
What's after?
HX plus
A, B, C, D, E, F, G.
HX plus
Fantastic! That would be the idea. Wow, I just spit all over the floor. This is the idea. Show of hands, feel okay with this one. This is why we're not doing this, because this is crazy. But you could, if you really wanted to. You could find your common denominator, and you could figure out your A, B, C, D, E, F, G, H, I, L, M, N, O, P, whatever you get out of there, and you could do your partial fractions.
There's an easier way?
There's no easier way. This is it. This is the
You
partial
can't do
fraction
the
reduction
chain
for
way.
this. Or decomposition, as we say. Now, fortunately for us, this one should be substantially easier than this one. We have a lot less fractions to deal with. What I want to know is, does this actually make sense to you guys?
Yes.
So we count our powers, make sure you have that appropriate number of fractions. Make sure that you don't do silly things like put a bx plus c here. Don't do silly things like forget to do the x plus e. Don't forget the x's. It's always going to be one less degree than whatever power that is. This counts as linear. You don't need a cx plus d here, but for every subsequent one where we have our irreducible quadratics, you definitely do need that. Any last minute questions before we get on to our actual example? Okay, the rest of this thing is going to take us a while, so I'm going to erase this because I need the room. But let's go back to this one. So if we're looking at this, then what we know is that x cubed minus 2x squared plus 3x plus 2 over x times x squared plus 1 squared can be reduced into some partial fractions, or decomposed into some partial fractions. Question: is the degree of the numerator less than the degree of the denominator?
Yes.
Yeah, this counts as x to the 4th, here's x to the 5th, that's more than x to the 3rd, that's great. So we don't need to do long division or anything like that. This is nice because that would be very hard to do with this problem. We don't want to do that. We don't have to redistribute and then refactor. Okay, can you tell me, actually, you know what, why don't you do it? Why don't you write out the fractions that you're supposed to have here? I think you guys are all at that level. Go for it. I know there's at least one. How many in total are we going to have?
3.
3.
Power 1, 1, 2, 3. Yep, you're right. Can you tell me what the denominators will be? Tell me what the denominators will be. First denominator, what is it?
X.
Second denominator.
X squared plus 1.
Perfect. Last one?
X squared plus 1 quantity squared.
Fantastic. That's exactly right. Show of hands, you get the denominators perfect. Good. So repeated quadratics work just like repeated linears. You just put the factors until you reach the largest power. So here we have x to the first, no big deal. We have x squared plus 1 to the second. Well, we need our first power, we need our second power. Now let's fill the numerators out, make sure we got those right. What's the first thing we're going to write here?
A.
Is this going to have x's up here?
Yes.
It's a quadratic. It's going to be bx plus c. This one, it's also quadratic.
Dx plus c.
Did you get that?
Yes.
Does it make sense to get that?
Mm-hmm.
We have linear, should just be an a, 1 power less, so 1 degree less. Quadratic should be 1 degree less, x's. Quadratic should be 1 degree less, still have an x. Show of hands if you feel okay with this one. Are you sure? You positive? This is big time, right? If you don't get this, are you going to get your problem right?
No.
That's an issue. Okay, we got to make sure this is perfect. Now, moving on. What's the next thing we do after we figure out how our rational expression is going to be decomposed into partial fractions? What are we going to do?
Find a common denominator.
Let's find our common denominator. Why don't you go ahead and do it? See if you can do it. I'll do it up here in just a second, so I'm only giving you a little bit of time. Did you get it back there? So remember what we do? We look here, we multiply by the missing factors just like any other time in the world you would ever find a common denominator. Just like in algebra. It is algebra. This is all algebra. Okay, I know I've said it about 50 times so far, but your idea is to find a common denominator between here and here. If you can do that, then if the denominators are the same, your numerators must also be equal. Therefore, when we multiply by the missing factors, we get that common denominator automatically. That's why we don't write these denominators here. So we're going to have numerator equal to our new numerator. What I do, I look here and I look here at each individual fraction. I just multiply by what's missing. So I know I'm going to have a, and the thing that's missing between here and here is my x squared plus 1 squared. You guys follow me on that one?
Mm-hmm.
Between here and here, well, be careful. I know some of you guys hate parentheses. I don't know why you hate them. They're friendly. When you have bx plus c, you got to have parentheses there. You will be distributing. So a times, well, I'm missing this whole x squared plus 1 squared. Got it. Bx plus c, okay, I'm missing. What am I missing between here and here? What's missing?
X and 1
And a
factor of x
factor
squared
of
plus 1.
Good, I am missing x for sure. And then I like how you said that, 1 factor of x squared plus 1. Let's make sure. I don't have the x, so I got that now. I'm missing the square. So I need 1 more factor of the x squared plus 1. If you multiply this times this, it should give you this. If you multiply this times this, it should give you this. That's how this stuff works. So you're just multiplying by the missing factors. You guys okay with that so far?
Yeah.
And lastly, we have a dx plus e, again in parentheses. So here we were missing this guy. Here we were missing x and 1 factor of this guy. Here we're missing what? So it's just got to be dx plus e times x. Show of hands if you feel okay with that. Perfect. Now, I think I mentioned this earlier. When you have these quadratic factors, it's not as easy as when you have the linears. With the linears, it was real nice because you could plug in numbers a lot of the times and eliminate entire terms, like entire sections of this. You can't really do that all that well here. There's one number I'd probably plug in if I wanted to, just really quickly. I'd plug in probably 0. If you plug in 0, this whole thing's gone. This whole thing's gone because x's would be 0 here. This would be 1. 1 squared is a. If I plug in 0, I get 2. Right off the bat, I know that a is 2. Does that make sense to you?
Mm-hmm.
So I'd probably do that first. So if I do x equals 0, I know that 2, so 0, 0, 0, here's 2. Here's 0 plus 1 is 1. 1 squared is 1. A times 1 is a equals 2. all this stuff would go to 0. 0 times everything would be 0. 0 times everything would be 0. So right now I know A is 2. Show of hands feel okay with that logic. If you didn't do that right away, it's going to be very apparent to you later anyway, so it's really not that big of a deal. What do we do with the rest of this junk? You distribute all of it. No, here's the problem. If you're like, well, wait a minute, why can't we just plug in? Okay, tell you what. Give me a number here that you can plug in that makes it 0. I'll give you $1 million if you don't use complex. Dang it. Yay, I win. Yeah, we're not talking about complex analysis, are we? That class is horrible. Yet. That's in upper. That's later. Okay. So no. Can you plug in anything to make this 0?
No.
No. Can you plug in anything to make this? I don't know, because you don't even know what D and E are. So, no. The only thing we could plug in to help us here was 0. We're done with that, so you're left with...
Distribute.
You can distribute it. Yeah. Distribute it. Go for it. Distribute it. And hurry, because we're out of time. So I'm going to leave this off to the side here. Okay, I know A is 2. That's actually going to help us a lot. That's good. Oh my goodness, wow. This will be fun. You're going to have to double check my work too, so 'cause sometimes I make mistakes just like you guys. I hope I don't.
You mean like distribute it all?
Everything.
Like all of
You
it?
gotta use PEMDAS.
What about just the first one? Are we good? X to the 4th plus 2x squared plus 1, and then A. Did you get the first thing like this too?
Yeah.
Okay. I know it's going to be a plus, so let's see. Did you get that for the second one? Same thing?
Yeah.
Did you? I want to make sure I'm right too, so don't leave me hanging here. If you got something different and I did it wrong, you let me know.
Wait.
That's what I got.
Isn't it?
Because of the
Oh, the
X.
X. I got that too.
Cool.
The X, man.
Okay, this one should be easy. Okay, all right, good, got it. Did we get that? That's all distributed. You, of course, might take a little bit more time and do this and make sure that you're actually right, because it makes no sense to do this and get it wrong. Otherwise, your problem, it's your smoke. You spend 30 more minutes on this to get the wrong answer. That sucks. So make sure this is absolutely correct. What do you do now?
Combine like terms.
Kind of combine like terms.
The
You
like
factor
terms,
out
yeah.
the like terms here. So we look for our like terms, and we do x cubed minus 2x squared plus 3x plus 2, no problem. And then we collect them. So I like to circle them. I know that that's kind of, well, why are we circling them when we're in calculus 2? But I don't like to forget any. I don't like to lose them. So I circle my like terms here, like this one and this one. Please remember that you're not factoring out the constants with your variable. You're literally factoring out just your variable. So if you had a 2 here and a 2 here, you leave it with the A and the B, because that's going to be a system of equations. All I'm looking to have you guys do is do this. A plus B, do all the constants, A and B are constants here, and then factor out the x to the 4th. Does that make sense to you? Yeah. And we keep on going. So I'm going to cross those out. I don't want to ever make the mistake of writing it twice or forgetting one of them. After that, I'm going to look for any of the cubes. Do you see any cubes?
Yes.
Trust me on this, you're going to love it when there's only one of them. Seriously. You'll see why in a second. I wrote C. I thought C. I don't know why. It's a 3. Man, yeah, if I write a C when I think of 3, I get PO'd. C3P, whatever. Come on, that was good. Okay, so I'm such a dork. So fourth's gone, cube's gone. I get a 2b or not 2b, C3PO. All I need is R2 and a D2, and we're good. I'll start using R's next time.
You just need to make one with that many fractions.
No, I don't want to do that. Okay, our squares. So with our squares, I've got, notice what I'm going to do. I'm not pulling out the 2, I'm going to leave the 2 with the A. So a 2A, and then a B, and then a D.
Shouldn't it be minus 2?
I don't think so. It's a positive.
Oh, I'm sorry.
I don't see any negatives up here.
Yeah,
so
no.
we're kind of fortunate as
I
far as
wrote
that
a
goes.
negative, I'm sorry, my mistake.
Yeah, it sucks when something calls you out on that, doesn't it? Anyway, square.
C plus E X. Oh.
So we got our fourths, we got our cubed, we got our squares, we got A, 2A plus B plus D, and then x squared. Now we're going to look for our x's. I've got that C and my E, so plus C plus E x, that's nice. And then lastly we have our, don't forget that A, that plus A at the very end. Oh goodness, okay. What I wanted to show of hands if you're okay on the algebra of it. Is it going to take you some time?
Yes.
But most of this is kind of algebra. When we get down to the trig, it goes very fast, and that's nice. You're going to know how to do all the trig and all the integrals, no problem. There will be trig in a lot of this, by the way, trig subs. Or there's going to be inverse trig function, like a tan inverse or something, because when we get down to this guy and this guy, you're going to be splitting that up. You'll have constants over x squared plus 1. You're going to get that. So be prepared for it. That's why we covered all the previous sections. Now, a lot of these are going to be nice and easy. Here's what I can show you. Do you know that your coefficients have to match up?
Yeah.
So for instance, when I'm looking at this, I'm looking here. My only constant is A. You got it?
Mm-hmm.
My only constant over here is, therefore, A must equal 2. We already knew that, but do you see how this really didn't help us all that much? It gives it to us right here anyway. So let's list them all out over here. I know that A is 2. So we got our A. Let's keep on going. What's another easy one that you see? I would look for C. I'd look for all the individual ones. Look at the C. I've got Cx to the third. You with me? Cx to the third. Look at my x to the third term over there. What's the coefficient of x to the third?
1.
Therefore, if I have an x to the third here, and this is my only x to the third, how much does C have to equal?
1.
The coefficients must be equal. So coefficient here is C, coefficient here is 1, therefore C equals 1. This was kind of nice, right? Not that hard to do. No serious systems of equations. It looks like it's going to be ridiculous, ends up being really easy. You guys okay with that one?
Yeah.
Then I start looking for stuff that's going to be easier after I come up with these basic ones. So A got 2, C got 1. If I see C and E, well, now I can figure out E really easily. Can you tell me what C plus E has to equal? What's C plus E? Let's see if you're going to get this. C plus E has to equal what?
3.
3, sure. C plus E, x. Here's my x. Coefficient is 3. Coefficient is C plus E. Therefore, C plus E has to equal 3. Okay, if C plus E equals 3, can you tell me how much E equals?
2.
Good. C is 1. So now we're starting to use some of these basic substitutions. C is 1 plus E equals 3. Therefore, E equals 2. So I got A is 2. I've got C is 1. I've got E is 2. Can you figure out the rest of them from here?
Yeah.
Easily. Let's look at let's look at this one. Some of you guys aren't used to this idea. I've got A plus B x to the 4th, correct? Wait a minute. Crap.
That has to be equal to 0.
How many x to the 4th do I have?
0.
None. So if I have A plus B x to the 4th and I don't even have an x to the 4th, A plus B equals 0. Coefficients have to match. The coefficient of x to the 4th would be 0. So 0 equals A plus B. How much is A again?
2.
So 2 equals B. B equals negative 2. Hey, we're almost done. One last one. I left the longest one for last, not first, because I wouldn't know how to do it, right? I left this one for last, so I'm doing easy to hard. How much is 2A plus B plus D equal to? Why don't you tell me? 2A plus B.
Negative.
Perfect. So x squared, coefficient is negative 2, coefficient here is this whole thing. Now we're just plugging in the numbers that we already know. I know that A is 2, so 2 times 2 plus, how much is b?
-2.
How much is d? Don't know yet. So we're plugging in what we know. We knew a was 2, 2 times 2. We knew b was -2, so plus -2. Then we just work it out, simple algebra. 4 minus 2 gives you 2. How much is d?
-4.
Have we found them all? A, B, C, D, E. We got A, B, C, D, E. Hey, we got them all. Now let's go ahead and let's write out what these fractions are going to be. So can you go ahead and do that for me, please? So write out what this integral changes into. You should have the same number of fractions. Your denominator should be the same. Your numerator should be whatever coefficients you had, whether it's a constant or whether it's a coefficient on x. What's our first fraction become?
2 over x.
Next fraction.
2x plus 1.
Negative 2x.
Negative 2x. That's right.
Oh, okay, so we want to make sure our signs are correct, huh? All right, that's probably a good idea. So b is -2, so we're going to have -2x. Our c is 1, so a was easy. It's 2. -2x plus 1, got it. And our last one, let's do dx plus e. What's d?
-4.
So it's going to be -4x
Plus 2.
plus 2. Okay, quick show of hands if you feel okay with that one. Cool. Now we got to kind of move. So I got to erase this. You know, I'll do one more step, and then I'll erase all this stuff. Whenever you get these quadratics or linear quadratics, unless it works with a substitution, which is not going to happen a lot, okay, because of that constant, it's not going to happen. So what we're going to do here, because if it did, you'd have an x here. You're not going to do that, otherwise it would have been reducible. So it's not going to happen. What you do here, split up the fractions. You've got to split them up. So our 1, 2, 3 fractions are going to change to this. 1, 2, 3, 4, 5 fractions. You follow? Do not change your denominators ever. So we have 2 over x. Here's what I'm going to do. Please watch carefully. I'm going to have, notice how I didn't bring down the minus because I didn't change that sign. I don't want to do that. I'm going to have minus 2x over x squared plus 1. So I can leave this plus and have plus 1 over x squared plus 1. I'm going to leave this minus and do minus 4x over x squared plus 1 squared. And then I'm going to have plus 2 over x squared plus 1 squared dx. Show of hands if you feel okay with that one. Are you sure? So we're splitting it up. We got no problem. Split it. -2x over x squared plus 1. No big deal. We got plus 1 over x squared plus 1. We get minus 4x over x squared plus 1 squared plus 2. Notice how my denominators don't change. I'm not changing that. I can't split those, okay? But the numerators, yeah, we can. Now, I'm going to do this a kind of an interesting way. I'm going to rewrite this whole thing. I'm going to write this on the top of my paper and do each one right under it. You guys with me? So I'm going to have a lot of space here, but I want to make sure you're seeing that I'm doing each of these integrals separately. You follow? Okay, so keep this in mind. I'm going to erase everything else. Are there any other questions before we continue? Some of these are going to go very quickly. Some of these are going to take a little more time. There's nothing I haven't taught you how to do. So what I'm probably going to do is show you how to set the integral up and then let you go for it. I'll probably write it very fast up here what the answer is. But you guys at this point should know how to do all of these things. So let's see. By the way, can I pull out some constants here and you guys be okay with it?
Yeah.
So this changes to 2 times the integral of 1 over x. You got it?
Yeah.
Dx. I'm going to split up everything. This is going to be minus 2 times the integral. You can even leave the 2 because of our substitution we're about to do. X over x squared plus 1 dx. We're going to have plus 1 integral of 1 over x squared plus 1 dx. We'll have minus 4 You know what? I need more space for this one. Oh, that should be fun. Yeah, I need more space for that one. Plus 1 squared dx. And then lastly, we're going to have a plus 2 times the integral of 1 over x squared plus 1 squared dx. Oh my goodness, that's a lot. Let's make sure we're okay with it. We pull the 2 out, we got 1 over x dx. We pulled the negative 2 out, or the minus 2 out, we separate our integrals, we got x over x squared plus 1 dx. This one was great, just an integral of 1 over x squared plus 1 dx. Minus, we pulled the 4 out, we got x over x squared plus 1 quantity squared dx. Pull the 2 out, we got 1 over x squared plus 1 quantity squared dx. Show of hands, be okay with that one. Oh my goodness. Now, some of these are going to be very easy. I'm going to go through quickly. Other ones I'll show you specifically. This one and this one are the ones you're worried about a little bit. The rest of them are going to be piece of cake. So, let's look at our cake. Can you do this integral?
2 ln.
2 ln absolute value of x. No problem. That's an easy one because we have a definition of integral of 1 over x dx is absolute ln absolute value of x. What would you all use for this? Just do a u sub. If you got x, so it's basically either going to be ln, a u sub, or it's going to be a tree. That's it. So with this stuff, we're going to do, well, u. u equals x squared plus 1. du equals 2x dx. du over 2 equals x dx. So when we go for that, we have integral of, notice we have x dx. This becomes our du over 2. So 1 over u, du over 2. Keep in mind we have a minus 2 out front. 2's are gone. We have minus ln absolute value x squared plus 1. Look, I did that one really fast, but I want to make sure you guys are okay with it. Are you okay with it?
Yeah.
You sure? So this was u, no problem. Basic substitution, x dx is du, right, over 2, right here. 2 with the 1/2, gone. Integral of 1 over u is ln absolute value u, plug the u back in. I know I'm going fast, but you guys should be able to follow that, or at least do it on your own. You okay with that one?
Yeah.
Okay, moving on. By the way, are the absolute values pertinent here? You would write them, and then you can eliminate them if you want to, because x squared plus 1 can't be negative. Now this one, this is an interesting one. This one you either draw a triangle for, or you understand that the integral of 1 over x squared plus 1 is tangent inverse of x. And that's very basic. This right here is tan inverse of x. No substitution, no nothing. That's literally it. Remember doing your integrals, the first thing you check for is check for your integration table?
Yeah.
That's right there. I'm check for it. That's tan inverse. You'd waste a whole lot of time if you were to draw your triangle. It's kind of fun. I like it. But it takes a long time to actually do that, right? Okay. Next one. What would you do here? Same exact thing. It'd be a u sub. So u would equal x squared plus 1. du would equal 2x dx. du over 2 equals x dx. Here's our x dx right here. So this would be our negative 4. We'd have an integral. We'd have 1 over u squared du over 2. Here's the big thing I want you to notice. Check it out. Notice how this was our u in here, correct? So we have 1 over u squared. Do you guys see where the u squared is coming from?
Yeah.
Is this going to be an ln?
No.
No. This right here is our negative 4. Sorry, what should be up there?
Negative 2. 2.
Negative 2. This would be u to the negative 2 du. We bring that up. This is not always an ln. Okay, this one's not. So negative 2 u to the negative 1 over negative 1. Or we get 2 over u. If I've done that right. Hopefully I did that right.
Oh, no.
So what that means, look what I did here, okay? I took the sign with it. I took my -4, I changed it to a -4. We did the whole thing and changed to +2. So I'm going to have a plus 2 over u. What's our u? X squared plus 1. That's the idea. Show of hands feel okay with that one? Okay. Now, oh, where are we at now?
The last one.
Last one. Last one. Last one is not in your basic integration table. We talked about this earlier at the opening of our class. This is one where you'd have to draw your triangle for. So you can think of it. Think of this as your hypotenuse. X squared plus 1. I'm going to do the whole class like that. X squared plus 1. And we got this leg over here is X. And this is 1. And if we got that thing, then we're going to be using a tangent. I'm not really going to do that. That'll be fun though, huh? You guys get me on the triangle?
Yeah.
That's got to be hypotenuse, right? If it is, yeah, we're kind of putting that square root up there. We know we can. We just change this to an x to the 4th. And then that would be a square root. Does that make sense to you?
Mm-hmm.
No, you can show that if you want to. I'm going to kind of sidestep that idea. Just think about it. Think, if this is part of a triangle, I put a square root around it, it's a hypotenuse. Then we have x and 1 because I'm trying to make tangent here. It's either tangent or secant or sine. I'm not going to cover it again because we already did. Equals x. Well, look at that. dx. Then equals secant squared theta d theta. Still okay so far?
Mhm.
Can we finish this example up?
Yes.
Okay, we're very, very close. What that means is that our integral here becomes 2, integral of 1 over tan squared theta plus 1 squared times secant squared theta d theta. So this is 1, okay, cool. This was tangent squared plus 1, whole thing squared. Dx is secant squared theta d theta. Show of hands, feel okay with that so far. Now what do we do?
Secant squared is squared.
So we're going to simplify it.
Yeah.
Simple word, simple word.
Secant squared theta. This is going to be d theta. I'm going to do this quickly. This right here is secant squared, correct?
Mhm.
Yes.
To the second power is secant to the 4th theta. Still all right so far? That means that this is 2, 1 over secant squared theta d theta. That becomes 2 cosine squared theta d theta. See where the cosine squared is coming from?
Yeah.
Hey! Do we know how to do cosine squared? 2, 1/2, 1 plus cosine 2 theta d theta. These are gone. We get, I'm just going to do the integral right here. This integral, therefore, is theta plus sine 2 theta over 2. We keep on going. Remember that with your triangles, I know we've seen this before, you can't have a 2 theta. You have to make this that 2 sine theta cosine theta. So we get theta plus 2 sine theta cosine theta over 2. 2's are gone. Now we need to change everything back again. So I'm going to do that over here. Once I get this. If tan theta equals x, then theta equals tan inverse x. Got that one. Can you do sine?
Yeah.
Sine is opposite, so that would be x over the square root of x squared plus 1 times, oh, cosine, look at cosine. Cosine is 1 over square root of x squared plus 1. So from here, this is all trig stuff. It should go fast for you guys. You should know it. This is, hey, 1/2, 1 plus cosine 2 theta, no big deal. 2's are gone. We have integral of 1 is theta. Integral of cosine 2 theta is sine 2 theta over 2. That's what a basic little use of. Sine 2 theta, no good. 2 sine theta cosine theta. So far, so good? Awesome. Well, then we have 2's are gone. Theta is tan inverse of x, no big deal. Sine theta, cosine theta, multiply. Sine, cosine. If you multiply, your square roots are going to be gone. This becomes tan inverse x plus x over square, no more square root. X squared plus 1. You guys see where the x over x squared plus 1 come from? We're multiplying here. So then we're going to do plus tan inverse x plus x over square root of x squared plus 1. Lastly, the only thing we do is combine some like terms here.
Square roots are gone.
These two things you can combine.
The square root's gone.
Oh, yeah, you know what, you're right. I'm sorry. Combine some like terms, so we have 2 ln absolute value x minus ln absolute value x squared plus 1 plus 2 tan inverse of x plus x plus 2 over x squared plus 1. Like term, like term, like term, like term. Done.